Good morning, Healing Hands Anatomy class. How is everyone today? If everyone can do their check-in, that would be awesome. Good morning. Happy Sunday. Happy Sunday. Good morning, Connected. I'm reading everyone's little good morning, Denise and all my colleagues. How was your week, dear? My week was great. I got my first tattoo yesterday and I'm never doing it again. How does that sound? Good morning. Good morning. Good morning. Hello, everyone. Just got off of work at 6 a.m. Oh my gosh. I'm so sorry. Hello, Cynthia. Saw the beautiful sunrise this morning. You know what? I kind of saw it too. It was beautiful. And back to work at 6 tonight. Oh my gosh. Good morning. Congrats on the fresh ink. Okay, well, I'm not sure I'll ever do it again, but yeah. I don't know. My daughter-in-law said, "Oh, you're gonna get addicted, Mom," and I'm like, "Yeah, doubtful." So, is it okay if I tell everybody what I got? It's on my forearm. It's a memorial tattoo for my husband. He used to write me cards and letters all the time, and I took a beautiful line out of a letter that he wrote, and it's in his handwriting, and they used his ashes in the ink. Yes, June, I got a tattoo. Yes, me, I got a tattoo. So anyway, and it's in his handwriting, which is amazing because he had the worst chicken scratch on the planet. But it says, "I'll love you forever, Kevin." So, yeah, I had wanted to do a paragraph that Dan is familiar with. It's on a picture that I have, but it came out to be 4 lines of chicken scratch and it just looked like chicken scratch. Cynthia, thank you for your comment. If you'd like to connect with me outside of class, please let me know. You have my cell phone number. Okay. I have information I can share. Yes, please don't hesitate to call me. You have my cell phone number. Anyway, so that's my story, and it doesn't hurt anymore. It just hurt when I was getting it. So, and I don't understand how people can get addicted to that, but I went with my son and my daughter-in-law. They just lost their first baby to a miscarriage, and they were getting memorial tattoos as well for that. And so it was very beautiful and very emotional, and it was amazing. My son took very, very good care of me and held my hand. And, you know, all women should give birth to boys. I'm just saying. Okay. Anyway, today is muscle contraction day. Good morning, Nicole. Today's muscle contraction day, one of my favorite days. One of my favorite days to teach. Nervous system is my absolute favorite. My laugh was for your comment of who people get addicted. Yes, yes. Yeah, I don't know. I don't know if I'll ever do it again, but I guess they say you get over the pain of childbirth, but yeah. Anyway, it's muscle contraction day. Oh, Naomi, I love being a boy mom too. We are their first love. Yes, yes, and I have a grandson, and same thing. Good morning, Cecilia. Glad to have you here. We haven't started yet because I've been yakking about my tattoo. and my personal life. And it's just so hard not being in the classroom with you guys. And, you know, we like to bring some personal stuff in. So if there's anything that you guys tell me that is okay to share, you know, just let me know. Okay? I'm honored to be here with you. Dan is here with us today as well. I don't know if he'd like to say good morning, but I'm honored to have him here for the day.
Good morning, everyone. Yes, I am here. I'm I feel handicapped with one single laptop monitor here at home. So yeah, if I can answer any questions to help out Denise, I'll be happy to. Thank you for turning in your homework. I appreciate it. Hopefully you got the response. Thanks. Got it. Thanks. Anyway, so good morning.
Yes, poor Dan has to work with one screen this morning instead of three, but he doesn't even have to be here because, oh, somebody's saying good morning, Martin. I love it. Erica, good morning, Martin. Does
Good
anybody call
morning.
you Martin?
No. Yeah, if they call me Mr. Martin, I don't think I'd answer. But Martin, like I said, Martin is fine though. I've been called worse no matter what. So yeah.
Well, I love what Emily calls you, your beautiful wife. I love what she calls you. I'd never heard anyone call you that before, and I won't say it unless I'm allowed to.
Oh, you could totally say it. I don't care.
Emily calls him Danny. Isn't that
Yes.
adorable? First
Yeah,
time I heard it.
my whole family calls me Danny. Yeah,
They do?
I'm Danny to my family. Yeah. So
Oh my
always
gosh.
always have been.
I didn't know that. I would never have thought to call you Danny, but
Yeah,
I might have to.
and you're more than welcome to. Like I say, I've answered to much worse, so yes, I'm used to it.
Ah. Well, just having your energy present in the background is very comforting for me. So I'm sure you'll come in and out throughout the day.
Absolutely. I have to. Before you get started, I have to say, muscle contraction is the start of the fun stuff. To me, this is everything else has been a kind of a setup. But this really illustrates how amazing the body is to show how muscles work on a molecular level, and it's just amazing, like I say. So anyway, I'm happy to be here.
Awesome. You see, Joanna's daughter's name is Emily, but she spells it in a really pretty way.
Amelie. I would pronounce that Amelie.
You would? There's no A there.
Mali. Yeah, I guess it sounds the same.
It's
Yeah,
Emily. Oh, you
that is a
boys.
beautiful way to spell it. Yes.
It is. All right. So here's our opening. Just remembering if you have a sound issue, close the other apps, reboot your device. Can't call the office because they're not there. Turn off the audio and then turn it back on. If that doesn't solve it, then you'll have to log out. Excuse me, Chrome is the preferred browser. Is that what it's called, a browser? You can
Yeah,
always
I
go to,
just loaded Chrome on this machine just to get to go to meeting to make sure everything was good this morning. So,
really?
yeah,
Oh,
yeah,
so
it's kind
you
of a new
actually can
machine.
go someplace and load Chrome on your computer. I
Yeah,
didn't know that.
it's really easy to do. You could probably even do it, Denise.
Really?
I think so. They give you
Oh,
step-by-step instructions.
you're so funny. Oh my gosh, everybody's a riot these days.
But then
Everyone.
again, we're still working on copying and pasting, so that's okay.
Yes. we are. We're still working on copying and pasting. Hey, did you get that handout to go up?
I did not. I did not. I think you should try now that the thing is going, and maybe it'll load now. I'm
All right,
hoping.
remind me as I get into the lesson. I have, can I, wait, if I have it here, I have a handout I wanted to give you guys, and I'm thinking maybe I can drag and drop it right now. I'm gonna try. Uh-oh. Oh, I closed it. Oh, never mind. I'll get it later. Okay. I guess we should start muscle contraction. What does everybody think?
What the
Sound
heck?
like a good idea? What the heck? Okay. I don't understand why my question box never opens on the last question. Okay, here we go. Okay, good morning. So it is muscle contraction day, and yeah, this is where we get, I mean, connective tissue though was amazing, right? When you're touching a body now, I mean, look how much fascia that we're actually touching. I have a great picture to show you in a little bit. Full body muscle, front and back from a Body Worlds exhibit, showing all the muscle. Of course, the deep fascia was removed from the top, but I'll show that to you in a little bit. So today's lesson is muscle contraction, and it is muscle contraction of skeletal muscle. So remember, we have 3 types of muscle in our body: skeletal, cardiac, and visceral. And we'll go over a little bit about each of those in just a second. Oh, good morning, Isaac. We're just now getting started, so you're good. All right, so our first type of muscle is skeletal. So it is responsible for moving the skeleton. It is under voluntary control within our nervous system, which we'll study next week. Within our nervous system, we have an autonomic nervous system that is under involuntary control, like your breathing and digestion, and circulatory functions, and but then we have a somatic nervous system, which is under voluntary control, meaning conscious thought is used to bend your elbow, or sit down in a chair, or run down the street. And so your skeletal muscle is the only type of muscle that comes under the voluntary side of the nervous system. All other muscle comes under the autonomic or the involuntary. It is known as striated muscles, muscle cells, because of what is actually inside the muscle cell. There are tiny fibers that make up small little motors that we're going to call sarcomeres later. We're going to build a sarcomere. And when you look at a muscle cell under a microscope, it has dark bands and light bands. It looks striped. And so the word striated refers to the striped look of a muscle cell under a microscope. So just so we're clear about a muscle cell, you can see them with the naked eye. Every little red fiber here is an actual muscle cell. So the functions of your skeletal muscle, of course, are motion, moving the body, your posture, sitting up straight or slouching over, heat production. I believe it's about 85% of your body heat is from actual muscle contraction. And then along with ligaments, the muscles help to stabilize joints. And I'm turning off my phone because it just beeped. I'm so sorry about that. Okay. So, yeah, I mean, have you ever been so cold that your body starts to shiver? Anybody ever been so cold that you shiver? Yeah, so what's happening is the involuntary part of your nervous system takes over because it's scared that you're so cold that it forces muscles in your spine to contract, and it's like they're contracting on both sides, and so they're causing you to shiver in order to create body heat. Okay, because we do get our body heat, a lot of our body heat comes from muscle contraction, which is why elderly people, mostly in nursing home, or any elderly person, as their muscles start to shrink away from not moving, from not being strong anymore, they have a harder time getting warm because they've lost a big heat production in their body. And conversely, on the other side, their sweat glands begin to shrink and die with age, and so they can't cool themselves off. So anyway, that was probably more information than you wanted, but that happens when I start yakking. I just keep yakking. Okay. Second type of muscle is smooth or visceral. So your viscera are your internal organs, your, how else can I say it? Your arteries, veins. You have smooth muscle everywhere. So here is the skeletal muscle. You can see the stripes here in this picture. So, and then you have smooth muscle cells down here. You can see that they are non-striated, so there's no striping there. Everything from your mouth to your anus, where you poop, is smooth muscle. It goes in all different directions. Your stomach has 3 layers of smooth muscle going in all different directions. Of course, this is under involuntary control. Involuntary, you don't have to think about digestion. You don't have to think about breathing. You don't have to think about your respiratory system. It just is under involuntary control. So your bladder, moving food through your intestines. And the difference, another difference between smooth or visceral muscle, these these cells contract very slowly, whereas our skeletal, they have different degrees of fast or slow and how they use their energy. Okay, so visceral is just has a nice slow pace, and you know, digestion's going slow and everything's just moving around slowly. What else can we say about smooth or visceral muscle? I don't think I have anything left. All right, so we'll move on to cardiac. And the picture stays the same because here you go. I don't know if you can see that they sort of have a little shape like visceral smooth, but with striations. And then they have these little, they're connected in a very different way. The cells are smaller, and then they connect to the next cell after, like in a long line. So definitely, cardiac muscle is a special type of a combination of smooth visceral and striated, yet it is completely involuntary. You are not in charge of whether your heart beats or not. Can you explain involuntary? Okay, so if you were to bend your elbow right now, just go ahead and bend your elbow. Those are skeletal muscles that are bending your elbow, and you chose to bend your elbow. That's considered voluntary, like you're volunteering to bend your elbow. When it comes to your heart beating and your intestines digesting, that's not something that you have anything to do with. It's just involuntary, against your will. It just happens. Okay. I see that you understand it, so I'm going to stop. Okay, so the heart is responsible for pumping blood, of course. You have two sides of your heart, left and right. It's very simple. And one side pumps oxygen-rich blood, and one side pumps oxygen-poor blood. So we only find cardiac muscle in the heart, and it's a beautiful combination of skeletal striated, visceral smooth, yet completely involuntary. Okay, so we're going to start with our definitions. Can I go back to smooth page? There you go. Are we good? All right. So we're going to start our definitions. Our first one is muscle fiber. I like to use muscle fiber because it gives you the idea that it's a long, cylindrical, like a rope. In fact, I'd never noticed it before, but this long red line here that we have in our PowerPoint, that could be a muscle fiber right there. you can see, and a muscle fiber is the same thing as an individual muscle cell. Okay, it's elongated, it's cylindrical. It can be as long as the entire muscle. So who knows what the longest muscle in your body is? Sartorius. Yeah, so if you were to measure your sartorius, I have no idea how long mine is, but just taking a little ruler, mine looks to be about 16 inches long. So I have muscle cells, muscle fibers in my body that are 16 inches long. So you can definitely see them with the naked eye. If you are used to cooking beef and you take a fork and after you've cut the beef, you shred it, you are shredding it into individual muscle cells or muscle fibers. They are the same thing. Okay, they're exactly the same thing. So in this picture, we have one muscle fiber that's being pulled out. If you remember when we looked at a type of picture like this last week on Connective Tissue Day, we have one fiber and it's coming out of a bundle of fibers. And then that bundle is coming out of a bundle of bundles is what I would call it. And a bundle of bundles is a muscle. Okay, a bundle of bundles is a muscle. So if you remember from Connective Tissue Day, I skipped that one slide because it would be easier to talk about it this week. The epimysium, the paramysium, and the endomysium. So last week when we were learning deep fascia, okay, when we were learning deep fascia, so Santali's question, fibers create muscle. So what we're going to learn today is that an individual muscle fiber, what we say is a muscle fiber, it's an individual muscle fiber. So you can see up here in the top of this picture, an individual muscle fiber. It's made up of tiny filaments, which is what we're going to learn about today, is the filaments that make up a fiber. So, but an individual muscle cell is a muscle fiber. But inside the fibers, we're going to learn about all the filaments, which are tiny fibers that help to create the ultimate single muscle fiber. Is that clear enough for now? Okay. Clear enough for now. Yeah, it's going to be, yeah, Dan said today is going to be fun. Yeah, it'll be a little challenging until we get the concept and I show you some really great videos. And just trust me, by the end of the day, you're going to all be fine. But don't hesitate to have me clear anything up as we go along, like Santali just did. So we're talking about deep fascia right now. And deep fascia has 3 layers. And this is what holds the muscle fibers together in a shape of a muscle. I'm being asked to go back again to this one. I'm not sure why. There's not a lot of information on it. Maybe, okay, got it. Awesome, okay. So we're talking about deep fascia right now in the 3 layers of deep fascia. So the epimysium, so epi means around, and whenever you see my, you're talking about muscle. So epimysium is the dense irregular connective tissue layer that surrounds the outside of a skeletal muscle. I really liked this picture because it actually shows this little pull away, which of course you can't pull this away because all connective tissue is connected to the next layer of connective tissue and the next and the next and the next. But this is just a really nice picture that shows this going around around the muscle cell. As we go in deep, now you'll notice that this epimysium is, remember, it's dense, irregular connective tissue. Who remembers what type of connective tissue a tendon was? Yes, dense regular, meaning the fibers are all going in one direction. So what I want you to capture in your mind is that this epimysium with the fibers going in all different directions rearranges itself when it becomes the tendon to the fibers going in all one direction. And then what type of tissue is bone? And what is that tendon attached to on the bone? I know this is not connective tissue day, but this is where we can really cement it. Remember, the tendon is attached to the periosteum around the bone, and the periosteum is attached to the bone. And all of those things are connective tissue: bone, periosteum, tendon, and deep fascia. So for the person that said hyaline, remember that hyaline is a cartilage, and we find that at the ends of bones where they go to attach to another bone. For the person that said dense irregular, that is what deep fascia is, and the tendon was dense regular. For the person who's saying loose areolar, for bone, bone was a solid connective tissue. Loose areolar would be the superficial fascia or adipose, okay? Oh, you're very welcome. Okay, so if we go deeper to the next layer, we have perimysium. So here's the other deep fascia layer that is surrounding bundles of muscle cells. So bundles or groups of muscle cells is the perimysium. And know that the epimysium on the outside, it continues in and it becomes the perimysium that is surrounding all these groups of muscles. Now, remembering how adhesions, so someone is asking, what is bone? So remember that when I taught you connective tissue last week, the things that were connective tissue proper, like cartilage and fibrocartilage and tendons and ligaments, all those came under a specific category of types. And then bone is a solid connective tissue, and blood and lymph are just considered a liquid connective tissue. Okay, they don't really have a category of dense regular or dense irregular. They're just a solid and then two liquids. But thank you for the question and for the clarification. So we are on paramysium now, and now remember how much deep fascia that we're dealing with when we're massaging. We have layers and layers and layers. And then the innermost layer, who remembers what's different about the endomysium? Oh, it's right there. The endomysium, which is what's wrapping each individual muscle cell. Endo means within. Remember, it was loose connective tissue, even though it's called deep fascia. It's a loose connective tissue because we need oxygen and we need the blood we need blood to get in, we need blood to get out, we need oxygen and nutrients and lactic acid to get out and waste products to get out and nutrients to get in. So each individual muscle fiber or cell is surrounded by a loose areolar connective tissue, but still referred to as deep fascia because of where it is. Okay? So these are the three layers of deep fascia that hold your muscles together. So while we're on this slide, earlier when I was talking about being able to shred cooked beef, can you shred raw beef or raw chicken or raw pork? Can it be shredded? Can we shred it? I'm going back to paramysium for a minute. We can't shred it. Why? Why can't we shred it? What's holding it together? Yeah, it's all connected. And what's holding it together? Fascia, exactly. The epimysium, the paramysium, and the endomysium, they're holding muscle together. We have to heat it. We have to create thixotropy by heating it and cooking it in order to melt away all the deep fascia so that you can shred your meat. So epi means on top of, peri means around, and endo means within. Remember the periosteum of the bone, it goes around the bone. Epi means on top of or above, and endo is within. All right, I'm going to go back to the next slide, which this is the last layer we just did. So this is really a great picture. It would be a little better if it actually looked like the bone had periosteum on it, but you know, I may get Raina to draw me a picture exactly the way I want it. If you've seen any art hanging around the school, I don't know if most of you know that those paintings are Raina's. She's an incredible artist. All right, love Raina. We love Raina. Yes, in fact, for those of you that, have you seen the big reflexology chart hanging in the classrooms? It's the real pretty one that's made with all the colors of the chakras. Yeah, that's mine and Raina's. I designed it. She painted it, and I have the original paintings in my office, and we sell those all over the world. We sell desk charts. There's one in every location. The one in Laguna, it's in the office. The one in Escondido, I think it's in the office. And Kearney Mesa, I don't know where it's hanging. But yeah, Laguna, there's one in the classroom. If you're in Laguna, it's in the classroom down by the tree. Yeah, it's in the classroom. Yeah, go look at the copyright. It's mine and Raina's name. And of course, Dan is our master printer. So it is a group effort with Raina and myself and Dan.
Oh, I was just waiting for the credit.
Oh, you were?
Yeah, not really, but yeah, I was wondering if you were going to say that.
Of course I am. And last but not least, Dan the man. Did I hear Emily in the background?
Yeah, she's actually talking to her mom in Bulgaria with
Okay.
Princeton. So yeah.
Okay, well, tell her that we all said hi.
Okay.
All right,
Yeah, Dan the
back to
print man.
muscle.
Yeah.
All right, is everybody good on these definitions? Understand that when you okay, so I'm going to talk about one more thing about cooked meat, and then I'll be done. All right. So if you've ever cooked a roast and you take it out of the pan and you put the pan on the counter or in the refrigerator, who can tell me, it probably mostly the people that like to cook, who can tell me the 3 layers that you get when it turns cold? Who can tell me the layers? What do you see on top? Yeah, on top is the solid fat. And then underneath the fat, who knows what's next? There's usually gel. And then on the bottom is liquid. Okay, so the fat we know came from the marbling in the meat. The gel underneath is the epimysium, endomysium, and paramysium. And then the liquid juices on the bottom are coming from the muscle cells themselves, the flavor of the meat. So yeah, so your connective tissue is that gel part. That's your ground substance. So when that gets cold, that's the jelly that forms is really what they used to use to make Jello before they came up with different sources to make Jello. All right, moving on. I think we already looked at aponeurosis last week. Just a little reminder of the large, flat, broad tendons made of dense, regular connective tissue. We have these 2 examples here, but then we also have latissimus dorsi has a large aponeurosis. And remember that an tendons have 2 jobs. They either connect muscle to bone, or in this case of the head, we have muscle, and then there's a bony attachment here, but then we have this muscle and no bony attachment, and then this muscle. So tendons can attach muscle to muscle or muscle to bone. Okay, so we're going to start our major definitions for the day. I know there's quite a few of them. And I'm going to make this as clear as I possibly can. Okay, so if what we're looking at here, our first definition when it comes to the actual contraction of skeletal muscle is a sarcomere. So you can see in this picture right here, this is a single muscle fiber. Okay, here's the tendon, here's the muscle with all its bundles. We've pulled out a bundle, and within that bundle, we've pulled out a single muscle fiber here, okay? And then from inside, we've pulled out what's called a row of sarcomeres. I think of a sarcomere like a little engine. It is the little engine inside your muscle cells that make a muscle contract. So it's called the contractile unit within a muscle fiber. So earlier, when someone asked about a muscle, do fibers make up muscle or something like that, they're really called myofibrils. So here's the word right here. We'll talk about it more, not to get really confused, but here is a Z line right here, and here is a Z line, and that's what borders each of your sarcomeres in your muscle cell. So knowing that your muscle cells can be as long as your entire muscle, I usually show the class, I want you to picture this, I usually show the class a piece of red yarn. And the red yarn has many, many fibers in it. And so the red yarn would be a single muscle cell, okay, or muscle fiber. Now, if I pull one of those fibers out, okay, one of those myofibrils out, what I have is one long row of sarcomeres like this red line here, okay? So if I were to start with a larger muscle cell, let me see if I can make a drawing here. So if I were to start with a larger muscle cell, yeah, I can't draw very straight, but I'm going to pretend this is one long muscle cell, okay? And inside of it is a bunch of these strings of sarcomeres, and they're all bundled together to make up one muscle fiber. And what this long string is a whole row of sarcomeres that go right next to each other, which is what we're seeing in this picture. Here's a sarcomere, here's a sarcomere, here's a sarcomere, here's one, here's one. And knowing that this is the single muscle fiber here, that would mean that if you were a sarcomere, you would have a sarcomere in front of you, to the left of you, to the right of you, below you, behind you. And sarcomeres are cylindrical as well, which is what makes a muscle fiber appear as cylindrical, meaning it looks like a piece of red spaghetti. Okay, so this is one long row of sarcomeres here. Each sarcomere is a little engine. What we're going to be learning for the next hour is what's inside the sarcomere and what makes it work to contract your muscle fibers. Let's see, somebody's asking questions. Don't you have aponeurosis from last week? Okay, let me see. I'm sorry if I get impatient with going back to slides. I don't mean to, but I've got to change my pen. Hold on. Okay. Okay, so what we have inside every muscle fiber, so think about a single muscle fiber, what it's made of, besides, you know, blood vessels and the connective tissue that surrounds it, what it is made of is several rows and rows and rows and rows of little tiny sarcomeres attached in a very long line. Okay, attached in a very long line. So this is a better picture because, so thank you for asking me to go back. This is one big muscle fiber. This is a single filament that I pulled out of this muscle cell here. And then I was trying to make little sarcomeres that sit right next to each other, all the way down the length of this filament. No, it's okay. It's okay. I didn't mean to get snappy. I'm getting on a roll about sarcomeres, and I get excited and I go into fight or flight, which, boy, we can't wait till next week to talk about fight or flight, right? So the rest of our definitions are what's inside the sarcomere. So you'll see the myosin, the actin, the Z-line, and all the things that make up this little contractile unit. And then when we're all done with these definitions, we're going to draw a sarcomere for you to have. I still have the sarcomere I drew 27 years ago in my class with Paula, and I find it to be extremely helpful. So we'll get started on those and then we'll take our first morning break. Let me erase the drawings. Okay, so who knows what makes up a muscle? Are they protein, or are they carbohydrates, or are they fats? Yeah, they're proteins. Yeah, they're proteins, mostly protein. Okay, proteins and chemicals. So everything we're talking, just about everything we're going to talk about in the next few minutes are proteins, okay? So myosin is, so if we look at this, so here again, this is a sarcomere right here. Remember, it said bordered by Z lines. Sometimes they're called Z discs. But the first we're going to do is myosin. Myosin is a protein. And the name of that protein is myosin, which is why it's called that, because it's named after the protein that it's made of. It is known as the thick filament in muscle contraction, the thick filament. So myosin, it's a protein. It's known as the thick filament. So if we look at this picture down here, the center of this line here, this pink one, It looks pink on my end. I don't know what it looks like on your end. But you can see that it's much thicker than any other of the filaments in our sarcomere here. It contains cross bridges, which we'll do on another slide, and that's what all these little bumpy arms are, is cross bridges. And there's another filament here that we're going to do in another slide that anchors the myosin to the Z line or the Z disc. Now, all I want you to do right now is simply follow along, and we're just talking about parts of an engine. Okay, we're talking about parts of an engine. We are deep inside our muscle cells and talking about the little engines. Okay. I'll give you a second to finish writing this down. All right. Let's go to the actin or the cross bridges. Oh, cross bridges. Here's a much bigger picture of our cross bridges. So cross bridges are sometimes referred to as oar-like projections on myosin. So they are also myosin. Okay, so they are made of the same protein. Sometimes it's called, and the pieces of them are myosin tails and then myosin heads. Okay, so they are attached to the thick filament. They are called cross bridges because they're going to cross over and attach to another filament, thereby creating a bridge, is why they're called cross bridges. They're also referred to as myosin heads, myosin molecules. All right, so they are made of myosin. They're called cross bridges. Okay. Does someone's hand is up? I'm not sure if you mean it to be up because you can't talk. Let me see. Raquel, your hand is up. Are you good? So the comment is they attach to another filament to create contraction. Yes, they do. Yes, they do. Our little motor, our little engine that could. Just confirming cross bridges. Excellent. Yes, we're going to see in our little engine that they do that. All right. Okay, let's go. I believe actin would be next. Okay, so actin is the name of the protein. Okay, so name of the protein. And it is known as the thin filament. So opposite of the myosin, it's known as the thin filament. Okay. Again, it's a protein. The protein is called actin, and you can see that it's this yellow one in this picture. I have all different pictures, so I'm afraid the colors will change. I try to get the best pictures I can. So, so the thin filament here, and if we look at the thin filament here, so here's the thick filament, this thicker reddish one, and then here's the thin filament, and you can see that they're anchored to the Z line. So they're anchored to the Z line. All right. All right, so we have only one, well, we have two more filaments to do, but I think we'll go ahead and take our 15-minute break. So go ahead and check out, and I will see you, I guess it'll be about a 13-minute break. And Dan, if you're listening, I sent you a chat and a text.
I am listening. I'm going to check it out right now.
Okay. And welcome back from break. Thanks for checking in. Okay, does anybody have any questions before we proceed? Okay, so no questions are coming up, so I'm gonna move on. Let me get rid of the words. Welcome back from break. Thank you for checking in. All right, let's move on to our next definition. So chitin, sometimes it's called elastin, but the protein is called chitin. It has an elastic quality to it, and it is that springy elastic protein that actually anchors the myosin. So it's this little swirly one here. And it's all swirly right now because it's at its resting shape right now. But what it does is when the muscles contract, this is what the myosin is anchored to, and the springy elastic part of it is what helps to bring your muscles back to their resting state after they've been stretched. So during contraction, the sarcomeres open and close, and chitin, that protein, is a part of that process. So this is another filament inside our little engine of our sarcomere. Okay, so we have one more, and we're going to go there on our next slide. It should be our Z lines. Did we miss Z lines? Oh, here it is. I'm going to do this one first, and then I'll go back to the other one, okay? I kind of want to do the fibers all together. I probably just keep forgetting to change this order on the homework. Not a big deal. So Z lines are also a filament, a little tiny fiber. Okay, and these are the borders of our sarcomere. So if you want to identify an individual sarcomere, you just look for the Z disc. Sometimes some books call them Z lines, some call them Z discs. And here's one Z line or Z disc, and here is the other one. And what do we see inside? We see, if we go here, we see our myosin, our thick filament. We see the cross bridges or the myosin heads. We see the chitin, and we see the actin. Okay, these are, and then we see the Z disc. These are all protein filaments that are within each of our sarcomeres. Okay, so they're called myofilaments. And when we put all those together, it's called a myofibril, that one long line of sarcomeres. And then if we bunch a bunch of those myofibrils together, that's what makes the individual muscle cell. Okay, is bunches of lines of sarcomeres. Okay, and we're going to just look at one sarcomere because that's really all we need to do is to look at one sarcomere to understand how our muscles contract. So I'm going to go back to the previous slide. And this is the sarcoplasmic reticulum. So remember on Connective Tissue Day when the word reticular came up for certain types of connective tissue fibers? So reticular fibers are finer collagen fibers, and they are a part of our connective tissue system. They're just finer. And sarcoplasmic is like plasmic refers to a fluid, and sarco refers to a bag. So this is a kind of like a fibrous bag made of connective tissue that weaves itself in and out of your single muscle cell all around those sarcomeres. Okay, and its function is to store double positively charged calcium, which is that Ca++ that you see there. Double positively charged calcium is going to be one of the chemicals that we use in muscle contraction. Okay, we have several chemicals that we're going to talk about as well. Okay, something is wrong with my question box. Dan, is yours okay? Hold on one second. No, there are absolutely no questions. They're gone. They're completely gone.
Can somebody type in a question? Somebody say something. Up. Yep. I'm getting. Okay. You're not getting that? Can you see this? Hello, test, test.
Yeah.
Hello.
I'm getting these now. I'm getting them now, but all the other ones were gone. Just gone. All this morning's questions are gone.
Oh, I delete mine anyway, so I don't have those anyway.
Yeah, I don't have time to sit here and delete them. Houston, we have a problem. Alexandra said she was having trouble saying that she was back from break. So I don't know if the question box is having a little issue, but everything is back. Can you repeat? Ca++, double positively charged calcium, is one of the chemicals that we use in muscle contraction. It's one of the chemicals. All right, so if anybody had, thank you for the test. If anybody has questions that I didn't answer, say something now while the question box is open, because I lost all previous questions somehow. All right, nobody has one. Okay. So the sarcoplasmic reticulum, fibrous-like material that is holding double positively charged calcium. Now it's holding it in a relaxed muscle. It comes in and out. And this is why calcium, one of the things our body uses calcium for, besides making strong bones, is muscle contraction and nerve conduction use calcium as well. Okay? All right. Okay, so it looks like we're at the time of day where we are going to draw a sarcomere. So if you like to draw the pictures with me, I'm going to have everything color coded. Okay, so you might want to get color coding ready, a piece of paper, whatever else that you might need to draw a picture. If Corey is out there, did you get did you get your question answered? I know Dan answered you, but we want to make sure you got the answer you were looking for. Okay. All right. So we're going to start. My slideshow has everything in order. So you could already see that we were going to start with our Z lines. Okay, so I'm going to use black. And I'm going to I am actually left-handed, but I can't do this with my left hand. I have to do it with my right hand. It's much like cutting and pasting, huh, Dan? Simple philosophy, but hard to manifest. So
Is this one of those things that should be designed for a special left-handed person tool or something?
right? There should be.
There should be, yes.
There should be. It is a right-handed world. All right, let's see what's next on our list. We have Z lines. And of course, I can't change the slide. All righty, Z lines. Oh, actin. So which filament was the actin? Yes, it's the thin filament. And what is it anchored to? The Z lines. Excellent. You guys are on it. Okay. Oh, I guess I have to choose a pen. All right. There's an actin. Okay, beautiful. Now remember, we can only draw in one dimension. If this were a true sarcomere, it would be cylindrical. And for every one myosin, there would be, I think, what is hexagonal? Is that 6? There would be 6 actins around it. So, but we can only draw in this one dimension. Okay, let's see what's next. That's our thin filament. Myosin. So we have myosin, and this is our what filament? Our thick filament. And we've got orange going here. So we're going to make a thick filament. Pretend this is all colored in orange. Someday I'm actually going to make a real slide, but I like drawing. This is really fun in the classroom because we can do it on the board. Okay, myosin, thick filament. I'm imagining that the next one is going to be cross bridges, but we're just going to have to go look. Yes, myosin heads or cross bridges. So because they're called myosin heads, we can assume that they are attached to the myosin. And so we're going to draw these little projections here. Now, if this were a true, oh, look at me. If this were a true, there would be hundreds and hundreds of these projections going in all directions, because again, for every one thick filament, there's 6 pairs of thin filaments surrounding it in a hexagonal pattern. And you're going to see this later in a video. I've got some great videos that are going to put all this together for you. Okay, so there we have some myosin heads. I'm sure your pictures look a lot better because I'm drawing with my middle finger. Same color. And why is it the same color? Because it's the same protein. It's the exact same protein, which is why I'm using the same color. It's all one type of protein. Let's see what's next. Probably the titin. Yep, or the elastin, titin or elastin. So at what place does what are the 2 places does the titin attach? Hopefully you're all saying anchored to the myosin and the Z line. This is very challenging. I'm doing my best. So you know that we would have another thick filament here, and we'd have another thick filament here. It's just a little time consuming to draw it all. So yes, anchors myosin to the Z line. You guys are doing great. Absolutely great. And remember, everything we're looking at here, Z line, actin, myosin, cross bridges, titin, they're all protein. Okay, they're all protein. This is the protein that makes up your skeletal muscle. All right, let's see what's next on our list. I think we'll be working with our chemical. Oh, sarcoplasmic reticulum. Okay, so sarcoplasmic reticulum would be hard to draw because it would just kind of wrap itself around this these rows of sarcomeres, and so they're within the muscle cell itself, and they wrap in and out of the rows of sarcomeres. So we'll just put a little sarcoplasmic reticulum off to the side here where it's not going to bother us in our drawing. So we'll kind of put a little bag here. And we'll put S and R. Just know that this would be wrapped completely around our rows of sarcomeres. Now, where the drawing is now, I want you all to get the mental picture that this side would be another sarcomere starting, okay? Thin filaments, titin, thick filaments. And on this side, same thing. We'd have actin, titin, and myosin going on this side because our muscle fibers are built out of rows and rows and rows of these tiny little engines called sarcomeres, also known as the contractile units of skeletal muscle. So there would be a sarcomere below it, a sarcomere above it, one in front of it, and one behind it. Unless you were the last sarcomere in the row, you would have sarcomeres all around you, okay? All right, I believe now we're gonna get into chemicals because our little sarcomere really can't do anything without chemical reaction. So we've already talked about one chemical, and that is double positively charged calcium. And who remembers where it's stored in our resting muscle? Where is it stored? Yep, in the SR. In the sarcoplasmic reticulum. So I'm using pink, and I'm going to put Ca plus. If you are a chemistry student or biology, you could also write Ca2 plus but because you want to know that this is double positively charged calcium. Don't ask me where the charge comes from because I don't know. All right, so double positively charged calcium is stored in a resting muscle. It is in the sarcoplasmic reticulum. All right, I'm looking at questions and comments. Excellent, lots of people said the sarcoplasmic reticulum. All right, we've got a couple other chemicals to get to. So ATP and ADP. Any of you already schooled in ATP? Some of you really smart people studied in college. So ATP is it is the energy source for muscle contraction. It's the energy source. It stands for adenosine triphosphate. Thank you, Raquel. Adenosine triphosphate. So that tells us that it has 3 phosphates. Okay, it has 3 phosphates. ADP is the byproduct when ATP kicks off a phosphate, and now it's called adenosine diphosphate. This is a renewable source of energy in your body. ATP is probably one of the most prolific, abundant chemicals in your body. Everything in your body needs ATP. I think of it like when you're going to see in the video how ATP splits as an energy source, and then it comes back together to create energy again. So in the videos, it'll make more sense. But we have ATP. Someone is commenting that it brings them back to biology class. Yeah. I got out of science in high school by taking basic aviation, and now I teach anatomy. So, you know, we never know where we're going to end up. For sure. All right, so ATP we have a certain amount of ATP at the ready. Oh, let me get my red color. Sorry. I'm so sorry. I'm dragging my feet here. I don't mean to be dragging my feet, but there's several steps I have to go to in order to use the pen and then not use the pen and then go back. So we have red. So ATP, we have a certain amount of ATP ready when we want to contract muscles. So there's a little ATP molecule. So ATP just kind of floating around the sarcomere. I'll just put ATP up here. Okay. Oh, that's a bad one. Okay. So adenosine triphosphate, this is our energy source for muscle contraction. ADP is the byproduct, but it is a renewable source of energy. ADP uses a creatine molecule to become ATP again. This is why bodybuilders or people who are trying to build their muscles sometimes take creatine. And then I know you guys have heard a lot about magnesium. ATP also has a molecule of magnesium connected to it. So it really, I learned from Robert North that it should be called ATP MAG. It isn't yet, but it helps us to understand why magnesium is so important in contracting and relaxing our muscles, is because ATP also uses magnesium in its in muscle contractions. So I've heard of Robert refer to it as ATP MAG, and I think he's really super smart. And if he says it, I believe it, and I'll go with that. Okay. All right. Now we have one more chemical, and we've given it a short name. We've given it a short name called the TT complex. When you were reading the chapter on muscle contraction, you probably saw the words troponin and tropomyosin. So they are a chemical strand. They're a chemical strand, and where they reside is they surround the actin in a relaxed muscle. They surround the actin. So I'm going to get some gray here, and I'm going to kind of surround the actin here. It's kind of like hiding it. This is not going as well as I'd like it to, but you get the picture. So it's two chemicals, troponin and tropomyosin. So one is the string and one is the little dots. I think most people pronounce it troponin. So this is a little chemical strand that is surrounding the actin. We're going to call it the TT complex because this is not medical school. We're trying to just get you through the little motor in your muscles. All right, the little motor in your muscles, your sarcomeres. So of course all of your actins would be, this is not going well. All of your actins would have this string of chemicals covering it, okay? So what I'm doing here is I'm setting you up, getting ready to contract this sarcomere, this single sarcomere, all right? Now, if you know anything about the chemicals in your body, they can only land and react in places that have what we call a receptor site for them. Okay, so all the cells in our body have receptor sites for different things. Glucose is a really good example. Glucose is your sugar, and when glucose mixes with an insulin molecule, they easily pass in to your cells because you have receptor sites. It's the same way viruses sneak into your body cells to make you sick, is they slip into your cells through receptor sites. They kind of trick our bodies into thinking they belong. So of the chemicals we have here, ATP, double positively charged calcium, and the TT complex, they're all going to interact with each other, and they're going to interact with the fibers. Okay, all these, I'm sorry, these filaments, myosin and actin and the cross bridges, they're going to interact, okay? And so the places that they're going to interact are called receptor sites. So I'm going to show you in the same color coding fashion what everything is attracted to, okay? We'll start with ATP, okay? So we have these ATP molecules floating around in our relaxed muscle. And when your muscle goes into muscle contraction, ATP is attracted to, so these little molecules here, their receptor sites are on the cross bridges. Okay, these are their little receptor sites on the myosin heads or cross bridges. This is the only place that ATP is attracted to. It does other things when it's in the cell, in the sarcomere, but its receptor site is on the myosin heads. Now I know I drew two on some, it doesn't really matter. So ATP is going to be attracted to the myosin heads. Double positively charged calcium, which is pink, is going to be attracted to the TT complex. So the receptor sites are on these little troponin, or one of the T's in the TT. And this is where calcium is going to be attracted to. I'll put one here. Okay, so when calcium gets let out of that bag, it's going to go straight to where it's attracted to. It's kind of like a magnet. Okay, it's like a magnet. And the last, and the last receptor site we have is not chemical. It is the myosin heads. Okay, so I'm going to go to my orange color. Now, underneath all of this troponin and tropomyosin, we have receptor sites on the actin for the myosin heads. So I'm just putting a few here. I'm putting these right on the actin. Okay. We are all set up. We are all set up for muscle contraction. So I want you to, you need a handout now, and if you need a couple minutes to get it, it is page, give me a second here, notes. I will show it to you. It's page 59 and 60, 59 and 60 in your 100-page packet. 59. So let me show it to you. So here it is. Can you see behind muscle contraction on the cellular level? This is what you need for the next part of the lecture. Muscle contraction on the cellular level. It should be page 59 and 60. I'm telling you right now, page 59 and 60. Oh, it's 61 and 62? I'm sorry. 59 then is another handout. What is 59? Is that the where do muscles get their energy from? Okay, so Dan, they already have the handout I wanted to put up. Sorry about that, you guys. So yeah, mine is not numbered, so I apologize. So muscle contraction on the cellular level, 61 and 62. Is there anybody that doesn't have it? All right, I'm not getting any answers that are no. So I will close the handout. Okay, so do you have your 100-page packet printed out? Your pages aren't numbered on your, I know Dan. I know Dan. Oh, you found it. Okay. Dan, isn't that weird that somebody's packet would not be numbered? Dan's probably playing with the baby. Oh, they're numbered. Oh, okay.
Yeah, they all should be the same because
I
they
know,
sent
but
out with it.
someone said that the pages weren't numbered, but they turned out to be numbered.
Okay.
Okay. Got it. Okay. All right, we're going to go back to the slideshow. And try to make this look whole again. Oh dear. Okay. So, I guess I could have my handout out. Oh my goodness, you know what, Dan? I gave Mindy my anatomy file. I gave Mindy my entire anatomy file and I don't have the handout. So,
Oh no.
I know, I don't have it to read, but can you guys be patient with me for 1 second? I'm going to print one out for myself. I forgot that I gave Mindy my packet. So sorry. The handout is page 61 and 62 in your 100-page packet. 100-page packet that we divided up and said that we'd be using these in order. All right, I'm going to go find it and print it out. Let's do file. I wonder if I can print it right from here. Or do I have to open it? Okay, everybody keep your fingers crossed. My printer likes to be cranky, but it looks like it's printing. I'll be right back. Well, apparently Sunday is a good day for my printer. Okay, let's get started. You guys are awesome and very patient. Okay, let's take a couple of nice deep breaths together. Hand on heart, hand on belly. Next deep breath, I want you to blow it out for as long as you can. Okay, I'm better. All right. So step one, everyone looking at step one, it says nerve impulse, acetylcholine. Nerve impulse, acetylcholine. So we're going to pretend that we have a muscle cell here. Here's here's the outside of the muscle cell. Here's the, well, that's a bumpy muscle. I'm so sorry. Okay, so here's the outside of our muscle cell. And here's a nerve coming down to meet our muscle cell. All right. And the chemical, because everything in our body is either a chemical or electrical impulse. Everything that happens in our body is either chemical or electrical, and especially in the nervous system. And so ACH, the abbreviation ACH, is the chemical that our bodies use to contract skeletal muscle. It also uses ACH to slow down our heart rate. So it creates movement in skeletal muscle, but it slows down your heart rate. So ACH is stored in the nerves. And when the impulse comes, that acetylcholine drips out, and guess what? It lands on receptor sites for acetylcholine. And then everything starts to break loose and everything happens. But we can't do anything without our nerve telling our muscle to contract. So we need the nerve impulse first. And this is just a little prequel to next week. All right, step two. The sarcoplasmic reticulum opens up. Hopefully we're all looking at this handout together. The sarcoplasmic reticulum opens up and it releases its stored double positively charged calcium ions. Now we know now that that calcium is attracted to the TT complex. So that's the first place it's going to go. All right. So when the nerve impulse comes in, this double positively charged calcium is going to run over here, and I'm just going to do one of them. And it's going to bind right here to this little binding place on the TT complex. Okay, now it has a really important job when it lands. And the reason I tried to draw this like a spring is because when the calcium lands on the TT, it rotates it. It rotates it around or off the actin, okay? And what was hiding underneath was the myosin binding sites, right? These little orange people here. So it rotates it off, and now the myosin binding sites are exposed. So who do you think is going to get really excited by this? Who's going to get really excited by myosin binding sites suddenly appearing? Yeah, the myosin heads, the cross bridges. Yeah, the myosin heads are going to go, woohoo! The actin is naked and I can touch it now. Woo! They get all excited, but they need something to help them move, right? They need something to help them move. So what's their chemical? What's their chemical? Hopefully you're all saying ATP. So step 3, because the TT complex is moved away and the myosin binding sites on the actin are exposed, the myosin heads are attracted to the actin because they're just like, whoa, I've been waiting for you my whole life. You're really, really pretty. Here I come. Shauna and I used to tell a great bar story, but I just don't even remember it anymore. Okay, so the binding sites are exposed, so I can't erase these, which is what I would like to do, but the ATP now binds. It comes over, and the myosin heads, they get themselves in a ready position when the ATP gets there, and then the ATP splits and it creates energy, and that energy is what helps the ATP, was what helps the myosin heads to reach out. Okay, so I'm gonna pull one of these out. They're gonna reach out and grab the actin. Okay, they're gonna reach out because they're gonna grab onto that binding site on the exposed actin. Now, and then they're gonna have what's called a power stroke, and they're gonna swivel, and they're gonna swivel in this direction, and this side is gonna swivel in this direction. So the little heads are going to swivel, and they're going to pull on this actin, and they're going to pull on this actin. And this is called the power stroke. And then now, imagine that this is all happening so fast that all of the myosin heads in different stages are reaching out and they're grabbing the actin, and then one is going to swivel, and as the next one is reaching out to attach, the one that swiveled is going to let go. It's going to get another ATP molecule, and as the other one is swiveling, it's going to reach out as the other one detaches. I'm going to show this to you in a video, so just be really, really patient with me and yourselves. And you can see all these little myosin heads reaching out simultaneously and in different order. They're reaching out and they're grabbing the actin and they're pulling it close to themselves. So can you see what's happening to the Z lines? Can you get a picture in your mind of what's happening to the Z lines? Can anyone tell me? They're getting closer together. Exactly, they're getting closer together. Your muscle fiber is shortening. No, they're not stretching. They're getting shorter. We're going to talk later about how muscles contract when they're lengthening, but most muscle contraction is muscles shortening. So the Z lines are coming closer together. They're getting closer and closer and close together as these chemical ATP are, what color do I have out? So yeah, they're reaching out and they're swiveling and they're detaching. And you can imagine this is kind of like when you play, what's the tug rope? Why can't I think of the words? I'm drawing a little blank here. Anyway, no, when you put two sides of people on a rope and you try to pull the other people into the mud, tug of war. Tug of war. Okay, think about tug of war, and you've got 10 people on each side, and at any given time, they have one hand on the rope, right? And then the other hand is reaching out forward in front of them to pull it closer. And then the other hand lets go and they reach out. Can you get that picture in your mind? That's what the cross bridges are doing. They're reaching out, they're swiveling, they're detaching, but at any given time, a lot of them are holding on because you don't want those to spring back. You want to bring those Z lines together. And then if you picture, okay, if you guys picture that there's a sarcomere over here doing the same thing, and another one way over here, and another one over here, the whole length of your muscle cells is just rows and rows and rows of sarcomeres. When a nerve impulse secretes ACH on a muscle cell, every sarcomere shortens. Every sarcomere is reacted. It's called the all or nothing principle, that every sarcomere in that muscle cell shortens. Now, depends on the force of contraction, how much they shorten. And you don't always engage every cell. When you think about what it takes to pick up, I'm picking up a ruler on my desk right now, but if I were to pick up the anatomy book, my brain would have to engage a lot more muscle cells to do that. So not every muscle cell is engaged when you go to pick up something. It depends on the weight of the object. All right, so let's look at step 5. New ATP molecules attach to myosin heads, cross bridges, to continue the process of attachment, swiveling, and detachment, eventually pulling the Z lines together on all sarcomeres, shortening or contracting your muscles. As long as there is double positively charged calcium present in the sarcomere, this muscle cell will be in contraction. Okay, and what's keeping the calcium attached to the TT complex is the nerve impulse. Okay, so the only way we can shut this process down is by relaxing the muscle. Step 7, shutting off the nerve impulse. When that happens, the sarcoplasmic reticulum, with the help of ATP, suck back in the double positively charged calcium. Once the calcium is gone, the TT complex moves back over the myosin binding sites and hiding the myosin binding sites from the myosin heads. And they detach, and then this is where the elastin or the titin comes in. It gently assists in pulling the Z lines apart and in bringing the muscle back to its resting length. So muscles don't exactly have a chemical relaxation. What's happening is the nerve impulse is shut down. So a muscle relaxer would actually shut down your nerve response or your nerve impulse so that your muscles relax. So it has its, the medication would have its binding site with the nervous system and not necessarily the muscles. Now it might cover the binding sites for ACH. I've never really looked into that. Why a muscle relaxant would work. So is there anybody, I know this was probably pretty overwhelming, but I'm hoping that having the handout and explaining the steps and that you're getting a picture and so question, is the actin or myosin shortening or both? Not at all. Not at all. They do not change length and they do not change shape. It's the Z lines that move closer together, shortening the sarcomere. And nothing happens to the actin or the myosin. Not at all. Thank you for the question. Okay. So the person who asked the question, it says, has left. I don't know if you're having trouble, Carolyn, if you're back yet. Oh, good. Okay. Okay. Good. 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 I know that sometimes you guys have trouble with your internet. So a couple of deep breaths. I think this is a very good time to take our lunch break. It is 12:21 on my clock. Let me see what time it is on the internet on my phone. It is 12:21, so I'll see you guys at 1:20 for lunch. So please check out. I'll just find a spot here. And I'll leave this up. At 1:20, I'll see you after lunch. Have a nice break. Please don't forget to check out. Hey, everybody, welcome back from lunch. Go ahead and check in. Excellent. I'm going to go ahead and play you some videos that will definitely cement up our lecture that we had before lunch about how sarcomeres work. So just waiting to see that everyone is back. All right, let's see, what will we start with? All right, what'd you think about that one? Good, I have a few more. So I'm just going to pick another one right now while we're in video mode.
The muscular, nervous, and skeletal systems interact to produce movement. Messages travel through the nervous system to the skeletal muscles that attach to bones throughout the body. The fibrous appearance of skeletal muscles is created by the arrangement of proteins inside the cells that form muscle tissue. Motor neurons of the nervous system connect with these skeletal muscles. Movement occurs through a series of steps. Impulses from the nervous system reach the neuromuscular junction. The neuron releases a neurotransmitter called acetylcholine. It binds to receptors on the muscle and begins a chemical reaction within its fibers. The muscle filaments slide across each other and the muscle shortens or contracts. This action produces movement. In order to produce movement in the body, the muscular, nervous, and skeletal systems interact in a process called muscle contraction. Muscle contraction begins when the nervous system generates a signal. A motor neuron conducts an action potential to its link with a muscle fiber. At the neuromuscular junction, a neurotransmitter called acetylcholine is released. This chemical binds to receptors on the muscle fiber. Acetylcholine receptors are chemically gated ion channels, and when acetylcholine binds, they open, allowing influx of sodium ions into the muscle fiber. This stimulates the sarcolemma and generates another action potential that travels through tiny folds known as transverse tubules. The action potential reaches myofibrils within the muscle fiber. Surrounding the myofibrils are membranous sacs called the sarcoplasmic reticulum. The arrival of the action potential triggers the release of calcium ions stored in the sarcoplasmic reticulum. They diffuse into the muscle fiber, and the next phase of muscle contraction begins. When an action potential travels to a muscle fiber, a series of steps begin within the fiber that result in contraction. Muscle fibers are organized into units called sarcomeres that contain two types of filaments. Thick filaments consist of myosin. Thin filaments consist of actin. Eventually, these two filaments will come together, creating a cross bridge. In response to an action potential, the sarcoplasmic reticulum within a muscle fiber releases calcium ions. These ions bind to a protein complex, causing it to shift and expose the myosin binding sites. The myosin head then binds to actin and the cross bridge is established. In the next step, ADP and phosphate are released. Their energy powers the movement of the myosin head. This step is called the power stroke. Actin moves toward the center of the sarcomere. ATP then binds again to myosin and it detaches from actin. ATP breaks down into ADP and phosphate, and the myosin head cocks back. Myosin heads continue to deactivate and reactivate. This causes the myosin filaments to pull together and slide across one another, contracting the muscle.
You use muscles every day to do activities. This woman is using muscles to breathe, circulate blood, and move her hand to take notes. Your cardiac and smooth muscle tissues are involuntary. You do not consciously control their actions. Skeletal muscle works under voluntary control. Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are anchored to the Z lines, the sarcomere shortens from both sides when actin filaments slide along the myosin filaments. Although the action between the filaments is described as sliding, the myosin filament actually pulls the actin along its length. The cross bridges of the myosin filaments attach to the actin filaments and exert force on them to move. This action is known as the sliding filament mechanism of muscle contraction. In this model, the sarcomeres shorten without the thick or thin filaments changing in length. A contraction begins when a bound ATP is hydrolyzed to ADP and inorganic phosphate. This causes the myosin head to extend and can attach to a binding site on actin, forming a cross bridge. An action called the power stroke is triggered, allowing myosin to pull the actin filament toward the M line, thereby shortening the sarcomere. ADP and inorganic phosphate are released during the power stroke. The myosin remains attached to actin until a new molecule of ATP binds, freeing the myosin to either go through another cycle of binding and more contraction or remain unattached to allow the muscle to relax. Muscle contractions are controlled by the actions of calcium. The thin actin filaments are associated with regulatory proteins called troponin and tropomyosin. When a muscle is relaxed, tropomyosin blocks the cross-bridge binding sites on actin. When calcium ion levels are high enough and ATP is present, calcium ions bind to the troponin, which displaces tropomyosin, exposing the myosin binding sites on actin. This allows myosin to attach to a binding site on actin, forming a cross bridge. Calcium ions are stored in the sarcoplasmic reticulum and are released in response to signals from the nervous system to contract. Neurotransmitter molecules are released from a neuron and bind to receptors, which depolarizes the membrane of the muscle fiber. The electrical impulse travels down the T-tubules and opens calcium stores. Calcium ions flow to the myofibrils, where they trigger a muscle contraction. As the actin and myosin slide along each other, the entire sarcomere shortens as the Z lines draw closer to the M line. As the sarcomeres in myofibrils contract, the entire muscle fiber will shorten. When muscle fibers contract in unison, a muscle can produce enough force to move the body, allowing you to take notes.
All right, how are those videos going for you guys? Excellent. I have more. I'm going to look at what ones I have. I might save a couple for later, but I'm going to look really quick. I need to talk to Dan and find out if any of these are crash courses. I'm not really sure. Let's see.
No, I didn't. I don't think I loaded any crash course videos, Denise.
Okay. Okay, perfect. Perfect. I wasn't sure.
Skeletal muscles, like the biceps brachii, attach to bone via connective tissue called tendons. Muscles are composed of bundles of muscle fibers. Each bundle is separated by connective tissues known as perimysium. Each fasciculus is made up of muscle fibers, which are separated by connective tissue called endomysium. Skeletal muscle fibers or cells are multinucleated and striated in appearance. Muscle cells are composed of subunits called myofibrils. Each myofibril is made up of several myofilaments. The two types of myofilaments shown in red are composed primarily of the protein myosin, and a thin myofilament shown in blue composed mainly of the protein actin. The repeating arrangement of thick and thin myofilaments serves as the fundamental subunit of striated muscle contraction. These subunits are called sarcomeres. A sarcomere contraction is represented by the shortening of the distance between the Z-lines. The sarcomere shortens because the thin filaments slide past the thick filaments. In 3D, each thick myofilament is surrounded by 6 thin myofilaments arranged in a hexagonal pattern. The 3D arrangement of sliding myofilaments is the microscopic basis of muscle contraction.
All righty. Let's see. I'm kind of ticking them off here one at a time. Let's see. Hope you're enjoying them.
Human locomotion and movement result from the contraction and relaxation of skeletal muscles. Muscles are attached to the bones by tendons, tough bands of fibrous connective tissue. Muscles are covered with epimysium, a layer of connective tissue. Muscles are composed of fascicles, which are covered with perimysium, another layer of connective tissue. Fascicles are composed of muscle fibers. Muscle fibers are formed by the fusion of muscle cells, and they can therefore be considered single multinuclear cells. They contain actin and myosin, proteins that produce contractions in the muscle. Actin and myosin are bundled in myofibrils, which have a characteristic striated structure due to the organization of the actin and myosin filaments. This is why skeletal muscles are also called striated muscles. The band that contains myosin is called the A band. The H zone, located within the A band, only contains myosin, while the I band only contains actin. When the muscle is stimulated, the actin and myosin filaments slide over one another. The I band and the H zone become shorter, and the muscle contracts. The molecular mechanism of muscle contraction is as follows. Stimulation of the muscle results in an increase in the calcium level of muscle fibers. Calcium ions bind to the troponin, which causes tropomyosin to move, and thus the myosin-binding parts of the actin become uncovered. Myosin binds to the actin, ADP and phosphate are released, and the myosin head bends and pushes the actin. Then ATP binds to the myosin head, which releases the actin. The ATP molecule splits into ADP and phosphate, and the myosin binds to the actin again. This process continues while the calcium level in the muscle fiber is high. When the stimulation is over, the calcium level decreases, and the troponin-tropomyosin complex returns to the default state.
Skeletal muscles come in different shapes and sizes, but the main structure of a skeletal muscle cell is basically the same. If we were to take a cross-section of a single muscle, we would find it is covered in a protective sheath or layer called the epimysium. The epimysium protects the muscle from friction against other muscles and bones. It also continues at the end of the muscle to form, along with other connective tissues, the tendon which attaches the muscle to the bone. Each muscle is made up of a number of bundles of muscle fibers called fasciculi. The fasciculi are contained within another connective tissue called the perimysium. Each bundle of muscle fibers contains anywhere from 10 and 100 individual fibers. A large, strong muscle, such as those in the quadriceps group, would have a large number of fibers within each bundle. A smaller muscle used for precision movement, such as those in the hand, would contain far fewer muscle fibers in each bundle. Each muscle fiber is also covered in a fibrous connective layer of tissues called the endomysium, which insulates each fiber. Beneath the endomysium is the sarcolemma, which is the muscle fiber's cell membrane, and beneath this is the sarcoplasm. This is a gelatinous fluid which contains glycogen and fats for energy, as well as mitochondria, inside which the cell's energy is produced. Each muscle fiber itself contains cylindrical organelles known as myofibrils. Each muscle fiber contains hundreds or thousands of myofibrils, which themselves are bundles of proteins called actin and myosin. These run the length of the muscle fiber and are important in muscle contraction. Surrounding the myofibril, there is a network of tubules and channels called the sarcoplasmic reticulum, where calcium is stored, which is also important for muscle contraction. Each myofibril can be broken down into functional repeating segments called sarcomeres, which are the basis for muscle contraction theory known as sliding filament theory. For more on physical education and sports coaching, don't forget to click like and subscribe.
All right, I think that was good for now. We have a couple left, but we can take a little video break later. Let's move on with our lesson. Before I erase this, does anybody want a picture of it? I can take out the 120. Just give me a second here. Oh, I can't take it out without erasing everything. So I'll give you a minute if you want to take a picture of this little, although I'm sure you have your own sarcomere drawn. Okay, so I believe the next part of your homework is asking about lactic acid. Is that correct? All right, thank you, ladies, for. Okay, so we have a handout we can go over too that talks about lactic acid and the production of it, but we'll get these facts down first. So lactic acid is a chemical byproduct of muscle contraction. It is not. Somebody is saying they don't see any question about that in the homework. Can somebody tell me what the question says? How does lactic acid interfere with muscle contraction? Does it say that? Okay, so Carlos, Yeah, Carlos, the question said, how does lactic acid interfere with muscle contraction? Your homework, Carlos, the written homework that you turned in. Did you turn in homework? Everyone is saying page 16. Page 16 of your muscle contraction homework. So, lactic acid is a chemical byproduct of muscle contraction. And a buildup of lactic acid happens when a muscle that is not conditioned to do a certain task, either because the muscle cells aren't built up to be strong enough, or you're doing a repetitive contraction that you're maybe not used to. And so when you think about all the chemicals that are happening, when you think about all the chemicals, you have ATP and ADP and phosphates. There's creatine in there. There's magnesium. There's sodium. There's double positively charged calcium, troponin and tropomyosin. There's a lot of chemicals that make your muscles contract. And just like a car engine, there is byproduct. Some of it is reused and some of it is not. So what happens, like, I don't know how many of you have a big event coming up and you think, oh, you know what, I'm going to start running every day, or I'm going to start lifting weights, and you start lifting weights that are much too heavy and you get muscle fatigue, and the next day you have some delayed onset muscle soreness and you can barely walk because you tried to run a marathon before training for one. That is a buildup of lactic acid. So lactic acid causes fatigue, it causes soreness, but physically what it does is a buildup of lactic acid actually interferes with the calcium that's stored in the sarcomere, but it also interferes with the cross bridges being able to attach or detach from the actin. So it can result in pain, in inflammation, weakness in the muscle. Now, for somebody who's working out, you know, they train and they build themselves up, they rarely get this lactic acid buildup, because when you start training your muscles in a healthy way, they slowly build up their ability to flush that lactic acid out. That's a natural process. We're all at some point in the day probably making lactic acid in our muscles, but our muscles are functioning on a level that they're actually flushing the lactic acid themselves. But if you overuse a weak muscle, or you decide you're going to run, you know, a marathon to lose 20 pounds before Saturday, you're going to fatigue those muscles to the point where they're going to have such a buildup of lactic acid that it's going to hurt to use that muscle. Okay. Of course, stretching, doing more exercise, because when you are contracting and relaxing the muscle through exercise, it helps, it helps to teach the muscle how to release the lactic acid. Stretching, exercise, drinking lots of water. You need lots and lots of water when you're building muscle. But massage. So I don't know how many times you've gone over someone's rhomboids, let's say. Rhomboids seem to get a lot of lactic acid built up in them. We have people, you know, doing desk jobs and with the forward head posture, and the rhomboids are trying to contract to strengthen the upper back and shoulders, and the nerves are, they get in a position where they're stuck on, and they're just creating contraction, 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 and you get a nice buildup of lactic acid. And then, you know, they get on your table and they talk about where they're sore and how their upper shoulders hurt, and you start fanning their rhomboids, and what do you hear? What do you hear? Oh, ow, like, oh my God, that hurts so good. Who's heard that term? That hurts so good. Yep. Now, what I want you've said it many times, receiving massages. Yes. Not only have I heard it, I've used it many times. Yeah, we're like, wow. And I teach my clients. I'll tell you exactly that feeling where you just feel this relief, even though it's a little bit painful. It's that hurts so good feeling because your muscle is immediately, you know, while you're fanning it, you're touching that sore tenderness of the overloaded lactic acid, but you're actually physically pushing it out. And what I want you guys to work on this week, if you're working on anyone, either in class or outside of school, is see how quickly the muscle recovers from the removal. This is why stretching is so important. Even though I'm an anti-stretcher, I still have to do it because I know the benefit. But what I want you to do is the next time you fan somebody's rhomboids and they say that, after you're done and you move on to another part of the back, come back to the rhomboids again and fan them again, and then ask the person how it feels at that point. And I think you'll see how fast muscles recover. All right, so that's a little, Ruby is asking me, what do I mean by an anti-stretcher? I just don't like to stretch. When I first went to college as a teenager, I was a dance major until all my brain anomalies show up and I wasn't able to follow that dream. And whenever we did stretching, like warm up stretching and cool down, I don't know, it didn't feel good to me. It wasn't like, oh my God, this is amazing. I would usually go to the bathroom or skip out of the cool down stretching. I don't know why. I'm not anti-stretching for anyone. I mean, I tell my clients all the time, the best ways to do certain stretches to relieve stuff. I'm just, but I was also a yoga hater for 20 years. And then I learned, that yoga's pretty cool. Yes, so we have another dancer in class. Yes, I loved, what I wanted to do was choreography. But unfortunately, life had a different path for me, which I love life's little twists and turns. I'm excited for my next twist and turn. Anyway, I'm going to give you that little exercise. Any muscle that you go over where they're like, oh my gosh, because you can tell when you're pushing out lactic acid, the muscle almost feels a little bit warm, a little bit swollen, and they're like, you know, how's the pressure? And your client says, oh, it hurts, but it hurts good. So what I tell my clients is hurts so good is extremely, is really good. When somebody has to tense up and holds their breath, then we've gone too far. We're on the other side of really doing any healing. We really want them to be able to breathe what we're doing. And I know there's some schools of thought out there that no pain, no gain, but I'm not that kind of teacher. I don't think we have a lot of those or any of those teachers at Healing Hands. You know, uncomfortable pain is an indicator that something's wrong. And if they can't breathe or relax through it, then we're pushing them too hard. And that's just my philosophy. All right. So lactic acid buildup, interference. Once the lactic acid comes out, there are chances, so keep this in mind. One of the reasons we tell people to drink plenty of water after a massage is we're flushing. You know, we're pushing all this stuff out of the muscles. We're moving their lymph, we're circulating their blood. If someone's particularly built up with a lot of lactic acid, when it goes into the bloodstream and it gets taken apart, and the pieces that are reused again are used and the rest are flushed out through our systems of elimination, it could make, sometimes somebody can feel almost like they have the flu. And so this is why we encourage people to drink a lot of water. Okay, after massage, really, really important to drink a lot of water. Hydrate, hydrate, hydrate. Okay, so any more? I think what I want to do really quick is I want to go over the handout that's page 59 and 60. I'm going to pull it up. I accidentally closed it, so I'm going to go get it. So page 59 and 60. Oh, why am I opening my email? It's not even time for a break and my brain's going cuckoo. Close email. Open file. Documents. So this is page 59 and 60. Since we just went over muscle contraction on the cellular level, I'm going to kind of read this to you, maybe make a comment here or there. So the source of energy that is used to power the movement of contraction in working muscles is ATP, the body's biochemical chemical way to store and transport energy. However, ATP is not stored to a great extent in cells. So once muscle contraction starts, the making of more ATP must start quickly. Since ATP is so important, the muscle cells have different ways to make it. Okay, you know that we're always going to get more ATP. These systems work together in phases. So they're using creatine phosphate, using glycogen, and then aerobic respiration. So creatine, all muscle cells have a little ATP within them that they can use immediately, but only enough to last for about 3 seconds. So all muscle cells contain a high energy compound called creatine phosphate, which is broken down to make more ATP quickly. So creatine phosphate connects with the P, the phosphate that came off the ATP. And once they connect, then that creatine can take that P back to the ADP and it becomes ATP again. This is why bodybuilders and people who are building muscle take supplemental creatine. In theory, it provides a lot more creatine to make more ATP faster. So creatine phosphate can supply the energy needs of a working muscle at a very high rate, but only for another 8 to 10 seconds. So glycogen, which is a fat sugar, fortunately, muscles also have large stores of carbohydrates called glycogen, which can be used to make ATP from glucose. But it takes about 12 chemical reactions, so it supplies energy more slowly than from creatine phosphate. It's still pretty rapid though, and will produce enough energy that lasts about 90 seconds. We don't need oxygen yet because it's taking a while for the heart and the lungs to get the oxygen to your muscles to make ATP. So this is great. Okay, so a byproduct of making ATP without using oxygen is lactic acid. So there's this period where we're working that muscle, waiting for the oxygen to come, that lactic acid is being made. You know when your muscles are building up lactic acid because it causes tiredness and soreness, sometimes referred to as the stitch. Using aerobic respiration is now, we're third in line, depending on how long we're trying to sustain our muscle contraction. Within 2 minutes of exercising, the body starts to supply your working muscles with oxygen. When oxygen is present, aerobic respiration can take place to break down glucose to make ATP. And we can get this glucose from several places. Anything left over in the muscle cells, we can take it from the intestines, glycogen in the liver. Glycogen is how the liver stores that glucose as a fat, and it will convert it back to glucose. We do have fat reserves in the muscles. And then in extreme cases, like when people are fasting or starvation, you can actually break down other proteins in the body to make ATP. So here's how it looks. So aerobic respiration takes even more chemicals to produce ATP than either the above two systems, meaning creatine and anaerobic. It is the slowest, but it can supply that ATP for several hours as long as you have a supply of glucose coming. So here's how it works. You've missed the bus and you start running to college for a 9 a.m. exam. The first 3 seconds of your run, your muscle cells use the ATP they had within them. For the next 8 to 10 seconds, your muscles use creatine phosphate to provide the ATP. Since you haven't made it to school yet, the glycogen system, which doesn't need any oxygen, kicks in. You're still not there, but finally aerobic respiration, meaning oxygen, takes over. So different forms of exercise use different systems to produce ATP. A sprinter is getting ATP in a different way to a marathon runner. All right, so using creatine phosphate, this would be the major system used for short bursts, weightlifters or short distance sprinters, because it lasts only for about 8 to 10 seconds. Glycogen, almost 1.5 minutes, so it would be the system in events like the 100-meter swim or a 200 or 400-meter run. Aerobic respiration, this is where we have marathon running, rowing, distance skating, and so on. Okay, so I hope you found this interesting. I find it fascinating. It's all about how our body uses different systems to make ATP depending on how long we're going to ask our muscles to be contracting. And then when next week, when we, or maybe today, or if we talk about muscle twitching, then that's going to come into play too. Oh, good. I'm so glad. Thank you, David. Yeah, I like this handout and I didn't know it was in the packet, so I'm really glad to hear that I put it in the packet. All right. Let's see where our PowerPoint is taking us. Next, it's almost time for our last break, but let's see what's next. Oh, okay. So we have 3 definitions here. We have agonist, meaning the prime mover in an action. And now you guys have your green books there, the ones you use on Wednesday night with Dan. So I will make sure that Dan, when you guys have the books open, shows you how you can study and agonists, antagonists, and synergists as a group of muscles. If you'd like to, Dan and I will talk about that. I don't happen to have my book right here, so I don't want to get you all confused. But an agonist is a prime mover in an action. There can be more than one. It's usually the strongest muscle in that action. The synergist, the third one, is assisting the prime mover. And then, of course, the antagonist, the one that's antagonizing the whole group, that's opposing the action. So I just want you to be familiar with the words. And we're going to go through a couple of examples. So I'm going to give you an action of flexion of the knee. And who knows a prime, what would be the prime mover that you think would be the prime mover in flexion of the knee? Okay, so hamstrings. We have biceps femoris, we have hamstrings. So rectus femoris would be extension of the knee. So let's look at what I have hiding under here. I do have the hamstrings as the prime mover. So what would be, I think antagonist is next. So who mentioned rectus femoris? Or even just quadriceps? Let's see if I have these in the right order. Yes, quadriceps would be a group that would antagonize. And what about synergist? What muscle in your leg assists the hamstrings in flexing the knee? Yes, Corey, excellent. Anybody else? So I'm going to go with gastrocnemius. Somebody did mention sartorius. I like to call sartorius the super servant muscle because it doesn't even have its own prime action. It helps everybody do something. So when you guys look at the green book with Dan on Wednesday, he'll show you how to tell the difference based on the print on which muscles are prime movers in your book and which ones are helpers. So here's another one, extension of the elbow. So extension of the elbow, what do you think is the prime mover? Okay, we have votes coming in. Votes are coming in for triceps, and I happen to think that you are probably correct. Triceps brachii. How about the muscle that would, there's several muscles that would go against it and antagonize it. It would be one of the elbow flexors, right? So let me see which one I picked. Oh, the brachialis. I picked the brachialis, and I'll tell you why. I picked the brachialis because the brachialis only crosses one joint, which means it's a stronger elbow flexor than biceps brachii. But brachioradialis could be on there. Biceps brachii could be here. I only picked brachialis because it is the prime mover in flexion of the elbow. And then who knows the little tiny muscle that helps? Oh, there it is. I don't even have to ask. That helps the triceps is the anconeus. Carolyn's noise has sound has cut out. Is anybody else having trouble with sound right now? I'm getting a lot of no's, Carolyn. Are you okay now? Everybody here is pretty clear. Why don't you turn your audio off and back on again? I'm sorry about that. I got a notice on mine that I might be having degraded sound. So, but I'm the only one talking. So I don't know if I have degraded sound, right? Because I'm the only one doing the yakety yak yakking. Okay. All right, I think we're good here. Like I said, I'll talk to Dan about showing you in the green book how you can study these. They're like all on one page. Your green book has elbow flexors and elbow extensors on the same page, and he'll show that to you on Wednesday. Maybe he'll even, I'm sorry, you might have the blue book, the book you use Wednesday night. I call it the green book because that's what color mine is, but it's the book you use on Wednesday night. Sorry. Some people have a light blue, some have a dark blue, some have a green, some have a white. They keep changing the color of the cover. So anyway, sorry, I should have said blue. I'm looking to see what we have left. Okay, we're gonna take our last 15-minute break. So I will see you at 2:35. How do the math for me, some people. Yeah, 2:35 is good enough. Okay, 2. 1:35. Okay, we're back from break. Thank you for checking in. Let's thank you very much for all of you checking in back from break. Thank you. Okay, so fast and slow twitch fibers. So earlier when I was talking about visceral muscles and how they use their energy really slowly, you know, digesting and breathing and all of that. I said that we kind of have a little bit of an option there with with our skeletal muscles. And so in skeletal muscles, it's called twitching, and a slow twitch muscle is where the muscle uses the ATP more slowly, so it can keep up the contraction for a very long time, okay? You would think about your postural muscles, okay? Your postural muscles, because they're, you know, they're keeping you standing, keeping you sitting. They have to be able to sustain a contraction for a really long time. So these are known as your red muscle fibers. They contain a lot more mitochondria and blood because they need to sustain the erector spinae, your neck muscles, for walking and for standing. And then we have our slow twitch, or fast twitch, I'm sorry, is when they use their energy really fast, their ATP, like your gastrocnemius when you're jumping or sprinting, shaking hands, your biceps brachii when you're, you know, it's a fast twitch muscle where you are using the energy really, really fast for short bursts of endurance. Now, I've lost my train of thought. Someone told me that when I lose my train of thought when I'm teaching, it's my husband pulling on my ear, trying to distract me. And I thought that was a really, really sweet thing to say. She said that she saw him doing it. And so every time I lose my train of thought, I'm kind of like, hey, Kevin, knock it off. I'm trying to teach, trying to do my job. So it makes me think of him. Makes me think of him like that. So, okay, so your type 1 fibers, which are your slow twitch, they have a lot of mitochondria, which are the engines that run your muscle cells, and they have a rich supply of capillaries, so they get a lot of blood to them to make a lot of ATP. They have a slow rate of contraction, and this is why they're known as your red or your slow twitch fibers. Your type 2 fibers, the fast twitch, they have few mitochondria, fewer capillaries, and a higher contraction rate, which is why they're known as your white or your fast twitch fibers. Now, your muscles generally have a 50-50 mix of the fast to slow twitch. Now, depending on how you train your muscles or partly your genetics, we know that postural muscles have a lot more type 1, the slow twitch, because we don't want them to, we need them to not fatigue. While your fast twitch fibers, they're a little bit more easily fatigable. Okay, so things like let's see, I'm looking at a list here. High endurance type 1 fibers, your slow twitch, your upper trapezius, levator, latissimus, erector spinae, quadratus lumborum, piriformis, sternocleido, all those things that help your body stand up, your adductors, medial hamstrings, rectus femoris, gastrocnemius. Those are a big group of postural muscles that are going to use their energy nice and slow in order to endure. And then the fast twitch, low endurance, scalenes, deltoids, your biceps and triceps, middle and lower trapezius, rhomboids, serratus anterior. So this list is in your book. It's table 8.3, which is really easy to find because that means it's in chapter 8. And you can look at the difference between the muscles. Okay? So that's what I love about this book. It is so geared to massage therapists. Now, again, sometimes your fast twitch they fatigue really easy, and you can train them to not fatigue really easily. But I was talking to someone the other day about people from Kenya, where I believe they pretty much win all the world's marathons because they have really fast twitch fibers in their legs genetically, and those fibers don't fatigue, which is why they have all those great bursts of energy, but they also have endurance. So it's really a part of their genetic makeup. So depending on the genetics of your muscles, whether you were talented as a sprinter or talented as a long distance runner. Okay, it looks like we're getting ready to do FYIs and pathologies. So we'll do this. We'll start these now. So anybody have clients or family members with fibromyalgia? Anybody in class with fibromyalgia? Dead air, dead air. Okay, so we have moms, friends, coworker, friends and coworkers. So fibromyalgia is it's a stress pattern that causes the immune system to be suppressed. So I'll talk to you about studies in a couple of minutes. It's characterized by intense pain in the muscles, fibers, in connective tissue, in all the supporting structures of the body, tendons, ligaments, connective tissues, joints. It can feel pretty systemic, like their whole body is sick when they're having a, let's say, an acute flare-up. Someone is commenting that whoever they know that has it, since she adopted a cat, she started to move around the house more and made her happier. So fibro, the word means muscle and fiber pain. So algia is the suffix for pain. So fibromyalgia, muscle and fiber pain. It's been around for a very long time. There were many studies done 20, 30 years ago when women were, and mostly women, sorry to say, had these debilitating pain syndromes, not being able to get out of bed, having disturbed sleep patterns, chronic fatigue, tender points, like not like trigger points. Tender points are different. They're in specific places. There's about 18 of them on the body that they used to use to diagnose women with fibromyalgia. When studies were done, it was found that some sort of a trauma had happened to the person within 20 years of coming down with fibromyalgia. And it has not yet been determined that it is an autoimmune disease, because I think it's felt to be brought on by a trauma to the body. That now the trauma could be a really bad car accident where the person's in pain for a long time, or even a difficult childbirth, or losing a child, or losing a spouse, or, you know, the death of a loved one. We started seeing fibromyalgia in war vets after Desert Storm, and it's finally being looked at a little bit more critically, that it could be a byproduct from PTSD, which is a trauma, right? Post-traumatic stress disorder, where the trauma changes people's sleep patterns and the way they breathe, or the way they, you know, live in the world. Post-trauma can be really, really challenging. I mean, I'm going through grieving the death of a spouse, and someone who's been in my life for 48 years, and now it's a more natural death than losing a child, which I can't even perceive that happening and what it's like, although I have many friends who have. But it's usually not confirmed as a diagnosis until after all other things like lupus, Lyme disease, multiple sclerosis, rheumatoid arthritis. It's kind of like they have to rule out all those other things. And they've also discovered high numbers of pain receptors in fascia. And we can actually see how much pain someone has been in or is in by a substance in their blood. And we'll talk about that on Endocrine Day. So, you know, everybody has trauma. Everybody has grief. Everybody has things that happen to them that are probably just horrible, but we're all made so different in how we react to those traumas. And I think that's why, you know, maybe, you know, we first saw it in women, you know, because of how women care for their emotional bodies. And so, but I think when it started to hit a lot of servicemen is when we really started to look at it a little bit more closely. Now, I know people who have fibromyalgia that are extremely healthy 95% of the time, but an emotional upset or catching a cold or something that kicks it back in and they go into acute flare-ups. We have a student saying that it has been debilitating for her mom. She is on disability. And yeah, it can, I mean, I have also known fibromyalgia people, clients friends who in a flare up, they can't even get out of bed. And so when I was a new massage therapist, I worked for a chiropractor for 1 year while I was finishing school. And I remember women coming in saying, I just got diagnosed with fibromyalgia. And the chiropractor would ask, how well do you sleep? And they would always say that they haven't slept well in years. And so I think chronic fatigue has a really big place to play here, because if we don't, as adults, we only have access to our human growth hormone, which I know is an endocrine thing, but human growth hormone is what helps our body to heal, not just grow. And we have access to it when we're sick, when we sleep, and when we're injured. And that's it. So if we don't sleep for a long time, muscles don't recover from that. They become flared up. And then you get into a syndrome of pain that is really hard to get out of. And I feel so much compassion for these people that suffer with it. And I know that there's nutritionally things you can do. I know that if you can get your hands on a fibromyalgia patient and just start working with them slowly, helping them improve their sleep by doing massage, pushing out the lactic acid, relaxing them, loving on them, I know that we could help, you know, heal the world. And I think we're going to see a lot more fibromyalgia since COVID. People were traumatized by the pandemic. They were traumatized by isolation. They were traumatized by people that they saw that were healthy one day and dead the next. And I think we're going to see a lot more fibromyalgia, and we are on the team of the best people to be available to help them. And so another comment is she's also a highly sensitive person and an empath. I wonder if there's a connection. You know, when people are empaths, and I'm not going to say it's their responsibility, because if you don't understand what being an empath is, you just feel the feelings of everyone around you. You know, getting a teacher to teach you how to close that off when you're in a group of people, close it off until you need it. feeling the feelings of others would be horrible, absolutely horrible. I know that there's great benefit to it if you develop the skill, but knowing how to turn it off, on and off when you need it, would be a really great skill. So there you go. I think we're going to see a lot more fibromyalgia, and we want to have compassion for these people. I know that as a young therapist, I tended to be a little bit judgmental about them, thinking that they could do something about it, but it comes through on so many levels that as I get older, I tend to understand the body's reaction to trauma, to stress, to grief. And it's definitely changed my perspective. So if that helps you at all, I'm glad, for me to say that. None of us wants to admit that we, judge other people, but I mean, we're human. We're human. So, all right. So rigor mortis is fun. It's the stiffness of death. So we talk about this because it has to do with the calcium and the ATP. So within maybe, let me think. Sorry, I have to have a big yawn because I'm not breathing enough. Several hours after a person's body ceases to have their vital force with them anymore, let's put it that way, the sarcoplasmic reticulum open up in your skeletal muscles and the calcium goes out, and we know that calcium goes straight to the TT complex on the actin, and it moves it away. And once it moves it away, all the cross bridges that were just waiting there reach out and they attach to the actin. But since your vital force is no longer in your body, there's no ATP to break the cross bridge. So after about, 8 to 12 hours, the body becomes stiff because all the muscles are in an isometric contraction, so to speak. Isometric contraction is when all the muscles, both the agonists and the antagonists and the synergists, everything is contracted. And so the body feels stiff. Usually by 24 hours, the SR, someone's asking what the SR is, the sarcoplasmic reticulum, in the sarcomere. In the sarcomere, the sarcoplasmic reticulum in the sarcomere, that's where that double positively charged calcium was stored. It was released from there. All right. So atrophy, when you break the word down, trophic or trophy means nutrition. So trophic or trophy means nutrition. And the prefix A means lacking or without. So the word atrophy means lacking or without nutrition. So when you do not contract muscle cells enough, muscle cells start to shrink. Okay, so we can make our muscle cells bigger, which is hypertrophy. We can build muscle by exercising it, because the more you contract your muscles, especially weight-bearing exercise, the bigger the myofilaments get. So you get more actin, more myosin, more mitochondria that are the little engines that run your muscle cells. But without nutrition, they start to shrink and fade away. And if you're in a cast for 6 weeks because you have a broken leg, your muscle is going to shrink down in size because it's not contracting like the other muscle is. So atrophy, a full atrophy, depending on your age, it can take quite a long time for a muscle to go into full atrophy. And when it does, muscle cells convert to adipose, to fat. So if you have, someone who's lived in a nursing home for many years and they're either in their bed or in a wheelchair and they cannot transfer themselves, they most likely are going to end up, before they die, with full atrophy in their, especially their lower legs, the gastroc, soleus, tibialis posterior, anterior, and so on, full atrophy. If there's just slight atrophy, like when someone's in a coma or someone's been in an accident, we can contract those muscles for you, and exercise will build them back up, unless, of course, the atrophy is very severe. So one thing I have not said today, and I'm being reminded of it right now, is when you are born with every muscle cell that you'll ever have in your lifetime. Okay, muscle cells do not renew. They do not regenerate. They are with you for a lifetime. Unlike skin cells, bone cells, blood cells, lymph cells, they are with you for a lifetime. So if you damage a muscle and the muscle fibers die, they're not coming back, okay? So muscles can get larger, muscles get smaller. Okay, Corey's asking me, Corey, will you check the spelling on that? Is that correct? I've never heard of that, that's why I'm asking. I love when you guys teach me stuff. So, okay, RHAB, exploding of muscle cells? Well, yeah, myolysis is when something is falling apart. Rhabdomyolysis, wow. I can't wait to look at this up. People may experience fatigue, inability to exercise, cramping, muscle weakness, abdominal pain, nausea, or vomiting. How do you know if you have rhabdo? The only way to know is through a blood test that checks for the presence of a muscle protein, creatine kinase, in the blood. If you suspect that you may have rhabdo, ask to have your CK levels checked. Symptoms can appear anytime after an injury. What's the most common cause? Potentially life-threatening syndrome resulting from the breakdown of skeletal muscle fibers with leakage of muscle contents in the circulation. The most common causes are crush injury, overexertion, alcohol abuse, and certain medicines. Wow, that's amazing. I've never heard of it. Well, I've heard of it, but I didn't know the name. Those muscle cells are never going to come back. If a muscle cell explodes or it gets crushed, now we can cut, shuts organs down, requires hospitalization. I'm reading all of this from you guys. Does it have miscolored urine? We'd have to look up signs and symptoms. It could go away on its own, but if you don't get treated, could be complications. All right, I don't know about the urine. You guys will have to look that up. I would imagine if you have, if a muscle cell explodes, that's it. Once a muscle cell dies, it's gone. Okay, people who've had radiation over an area, let's say they do radiation of a breast and the pec minor is right there, it causes what it's called muscle wasting, where the muscles shrink to very, very small. Okay, it's called muscle wasting, and you can get that from radiation. Also radiation fibrosis. So yeah. Wow. Well, thank you for teaching me a new, oh, somebody just made a comment and I missed it. Hold on. Sometimes you hear about the Navy SEALs going through training, going through a case of rhabdo due to overexertion. Okay, so those muscle cells will be gone. They can build the other ones up and strengthen their muscles, but aren't they usually pretty lean, Navy SEALs? Yeah, that's crazy. Well, I'm so glad to know something, but crush injury makes sense too. If you get a crush injury and it just squishes those muscle cells and they're just not going to come back. Now you can cut muscle, you can tear it, you can, I'm going to say in the old days, but, not 10 years ago, when they did a hip replacement, they literally cut the muscles in half. So the upper part of one muscle from the lower part, and they would just cut them right in half, open up that joint, replace it, and then they'd sew the muscle. Then they sew the muscle back together and it heals. What would be an example of loose muscle? What do you mean? Loose or lose? Loose or lose? The first one that you typed is loose. The second one is lose. You can't lose muscle by massage. You can't, you can't. And of course, the massage therapist is building muscle as they're working. Anyway, I'm not sure. Did I answer your question, Carlos? Oh, good. Okay. Phew. All right, let's see where we're going next. Lou Gehrig's disease. So remember the amyotrophic. So without muscle nutrition, amyotrophic without muscle nutrition, lateral sclerosis, meaning that the disease starts in the limbs. It's characterized by muscle spasticity, rapidly progressive weakness due to muscle wasting. It results in difficulty speaking, swallowing, and breathing near the end. The motor nerves that are affected when you have ALS are the motor neurons that provide voluntary movements and muscle control. Now we see a lot of ALS coming through like after head injuries, and it really could be traumatic brain injury. Alexandra, are you talking about rhabdo? Very fit people can have this caused by extreme physical exercise and dehydration. Okay, thank you. Thank you. So Lou Gehrig's disease, amyotrophic lateral sclerosis, or ALS, it's a really, really horrible disease. I took care of a couple of hospice patients with ALS, and near the end, the only thing they could do was blink their eyes. It's like you're locked into a body that can't move. It's really, really hard. Now, Stephen Hawking had a form of ALS that he ended up living many, many years with. The people that I know usually from diagnosis to death is usually not more than about 7 years. Yes, there's a comment by a friend passed from ALS. Another comment that, yeah, mentally they're all there. They do not lose their mental faculties at all. And so it can be a really, really horrible disease. Okay, let's see where we are.
I got to put my 2 cents in there, Denise.
Dan, that's right. Welcome in.
Thank you. Yeah, my mom had Lou Gehrig's disease, and it was like the worst. It wasn't like Stephen Hawking's, where it lasted many years. She was gone within, I'd say, within a year. From when it was diagnosed. Just, yeah, like I say, her mental, she just can't. You just can't do anything. And finally, her lungs, she couldn't breathe anymore because it didn't allow her to. Yeah, thanks. It was, yeah, it's an awful. And you know, they don't have a cure for it, unfortunately. So that's the tough thing. I just hope it's not genetic, you know, and passes it on. So anyway, yeah, it's tough. I don't know if they know what causes it, but maybe Denise could speak more about that. But like I say, they know that they don't have a cure for it.
Yeah, I don't know, and no, I don't know if, but it is an autoimmune disease where the body is attacking itself. Is there a particular age range that is affected? I honestly don't know. We had a young mom with 5 small kids on hospice with it in her 30s, and I knew people in their 40s and in their 50s. I met a man who had kind of like the one that Stephen Hawking had, and he's living, you know, lived a very long time. Someone is asking, does massage help in any way. Well, with my patients, they were ordered massage, yes, because they can no longer move their muscles. And so whatever's they could still feel though. So massage helped them feel better. You know, it only, if you'll notice in the description, it only attacks motor neurons, not sensory neurons. So the help is in the nice touch and how touch feels in that instance. And that's what I did for my patients, was when they couldn't move. No, they're able to tell you, you know, because like I said, my last patient, she loved the massage, and, you know, I could check in with her and ask her if it felt okay, because she could still blink. She could move one finger as well. So yeah. All right.
Yeah, for me,
Go ahead, Dan.
she passed before I became a massage therapist, sadly, so I wasn't able to even help her out that way. But yeah, that would have been really nice to give her a massage. Anyway, go ahead.
Yeah.
Moving on.
No, I appreciate your comment. I mean, you had direct experience with it, you know, in your own family member, and you know, me, myasthenia gravis is where my experience is, because this is what my mom has. My mom's had it for about 30 or 35 years. It is a neuromuscular disease that leads to muscle weakness and fatigue. And what happens is, so when we did step 1 of muscle contraction, step 1 was nerve impulse. And so if you remember in the drawing, the nerve impulse releases acetylcholine, and the acetylcholine falls on the muscle cell itself and activates muscle contraction. Now, when we're done contracting that muscle, any available acetylcholine is eaten up by an enzyme that is in our body on purpose to eat up the acetylcholine so that the muscle can stop contracting. And what happens in myasthenia is that enzyme overreacts, and it tries to eat the acetylcholine all the time. And so the muscle weakness and fatigue is very marked, because when my mom is in a flare-up, she can barely get up and walk, because her acetylcholine enzyme is just attacking her ACH. So it can be really debilitating, and, you know, completely changed her life. It's not necessarily something that she would die from. She's 87 years old, so I think she came down with it in her 50s. I would say she came down with it in her 50s. So, yeah. All right. Isotonic and isometric contractions. So I'm going to go to isometric first, and then I'll come back, because an isometric exercise, your muscle length does not change. So if you were to stick your arm out to your side, straight out from your shoulder, and squeeze all the muscles, this is a static position, and all of your muscles in your arm are contracted. Can you feel them be really tight? This is an isometric contraction. What you see in this picture is by someone holding the weight, and it's done in a static position where they're not flexing and extending their elbow. That would be isotonic. Isometric is when there's no change in length during contraction of the muscle. But all the fibers, depending on how heavy that weight is, all the fibers are contracting because it's trying to hold weight of that dumbbell in their hand, okay? So if we go back, so isometrics are done in all kinds of workouts. You know, when you go to Pilates, they tell you to zip up your core and tighten everything up, and everything in the front and the back tightens up. That's isometric. So no change in length, but yet the muscles are all contracting. Isotonic is muscle contraction that we're used to experiencing. It has two phases. It has concentric and it has eccentric contraction. Concentric is what we're used to thinking of. This is where the muscle actually shortens, okay? But earlier in the day, I said we'll see an example of muscles contracting as they're lengthening. So if we look at what's happening in this picture, okay, he's doing bicep curls, right? Bicep curls with resistance, okay? We don't get this just by bending, your elbow, because to bend your elbow without resistance, you're using some biceps brachii. To extend your elbow, you're using some biceps brachii. But if you have something heavy around you, like your anatomy book, and you put your hand out in front of you with your elbow bent, and put that book in your hand, you'll find that if you lower your hand, because of the resistance from the weight, it's like I describe it like your cross bridges are putting the brakes on. Your cross bridges are still holding on to the actin, but they're not pulling the actin towards them. They're slowly letting the actin move away from them, but the muscle is still in contraction, because if it wasn't, you would just drop the book. Okay, so by holding the weight or something heavy, the resistance is greater than the force the muscle is producing. So as the muscle is lengthening, it's staying in contraction. This is why working with weights, free weights, builds muscle so completely, because you're contracting both ways. You're contracting when you're coming up, you're contracting when you're going down. And depending on whether you're doing, so it's still going through the same process with the double positively charged calcium and ATP. Yes, Carolyn, it is. It's still going through it because we need those cross bridges to connect with the actin to keep the muscle from giving way and you dropping the book or you dropping the weight. So absolutely, it's just going in reverse. And I like to think of it as like putting on the brakes. Skid, 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 skid. Because if the muscle let go and relaxed for any reason, you would drop the weight, you would drop the book. Okay, so when you are closing the angle on the joint, if we look at just this example here, we're looking at just the biceps. If we had the triceps on the back, right now the triceps would be eccentrically contracting as the biceps is concentrically contracting. Does that make sense? Because there's a resistance. In this picture, you're going downward, so the biceps is lengthening, but it's still contracting, and the triceps would be shortening on the back. So it would be concentrically contracting. How does that feel for everybody? Does that feel okay? I hope I'm explaining it well. Can I go back for a bit? Go back where? Honey, the last one, the isometric? And explain? Okay, so the slide we went to first was isometric. So by holding the weight and not bending the elbow up or down, you're causing the muscle to still contract because the book is heavy, because the weight is heavy, or the book in your hand is heavy. So even your triceps, I don't know why they don't show the triceps, but the example I gave you was to, you know, stick your arm straight out, make a fist, and tighten all those muscles in your arm. And now feel the muscles, feel how hard they are. They're all contracted, but yet nothing, no, your elbow didn't flex, your shoulder didn't extend. This is isometrics. Isometrics. I think doing a plank is an isometric exercise, isn't it? It's where your muscles are contracted, but nothing's changing length. It's static. You're sitting still. I'm going to ask the experts out there. The bodybuilder flexing. Yes, it is. So a plank, if you know what a plank is, that's isometric. Nothing is changing length, but all your abdominal muscles, your front of your legs, the back of your legs, everything's contracting. So the bicep would be the agonist and the tricep would be the antagonist. Well, it depends on what action you're doing. If you're flexing the elbow, yes, air squatting like a wall sit. You do a 3-minute plank at least twice a day. Oh my God, that's amazing. I'm just learning how to do a 30-second plank for 3 times. Okay, so June, I'm gonna sneeze. I've got another one coming. All right, I want to go back to June's question. Thank you for the bless yous. June's question was agonist versus antagonist. June, we have to have an action before we can make that determination. So in flexion of the elbow, biceps is the agonist, triceps is the antagonist. If we were going to extend the elbow, that would reverse. So you're looking, the agonist is the prime mover in an action. And again, Dan's making notes about showing this to you in your book and helping you understand it more, because I know he's listening. Isotonic, so tonic, building tone, this is where you're either shortening the muscle or lengthening the muscle, but because you have something heavy in your hand, both muscles, both the agonist and the antagonist have to contract to sustain the weight of the object in your hands so that you don't drop it. Okay? Trigger points. Woo-hoo! So a trigger point. Oh, Dan, you wanna, I don't think, did we load that trigger point video?
Honestly, I don't remember if I loaded it, but I was planning
All right.
on, if not, definitely playing it on Wednesday night.
Okay, let me look while they write this down. Cross bridge physiology, sliding. No, it's not there. So Dan will, oh yeah, trigger point. Trigger point's there. Okay, so we're gonna show you another video for sure. Okay, so a trigger point is a hyper irritable spot within bands of skeletal muscles within the fascia. So I'm going to tell you the most common trigger point I see is right at the top of the scapula where levator scapula comes into the shoulder blade. You press there and they usually get referred pain out their arm or up the back of their head. Okay, so direct compression or muscle contraction can elicit both local tenderness and referred pain, which usually goes into a pain pattern that's different from the actual spot. Now, newer technology is letting us know that trigger points can be caused from an overload of ACH, acetylcholine, that chemical that contracts muscle cells, from chronic contraction, injury, or overuse. Okay, so ACH dripping because, and we'll talk about this next week, when nerves get stuck on and they just have a nice little drip of ACH, and that acetylcholine isn't strong enough to make a full muscle contraction, but it's enough to overload the area and cause trigger points and possibly ulcerations within muscle cells. So when a trigger point is really beautifully developed, it's going to refer pain to other places. And if you haven't had a trigger point class yet, I hear it's really fun. Or there's a great book out there, the leading authority on trigger points. I have to think, Travell, is that her name, Travell? They sell the book in the office, so you can look it up. So I'm going to go ahead and show you this video that Dan found.
Many people suffer from pain and physical problems. Very few people know that these problems are often related to trigger points. Understanding and treating trigger points helps to lessen pain and improve overall health. This video is a short explanation and introduction to the trigger point. A trigger point is a small muscle contraction which can be felt as a small nodule. Pushing on this nodule is very painful. Trigger points can exist in each muscle of the body. Multiple can exist at the same time. Often both sides of the body are affected equally. The trigger point keeps the muscle tight and weak, restricting the muscle's range of motion. A trigger point can actively cause pain, or it can cause no pain unless touched. Mostly this pain is sent to a different area of the body. This is called referred pain. Referred pain can make finding and treating trigger points difficult. Luckily, referred pain follows typical patterns that have been well documented. Let's take a closer look at the trigger point. A trigger point lies in a taut band. The taut band is a tight strand of muscle that feels like a cord, easily mistaken for a tendon. The trigger point itself can be felt with the fingertips when its location is superficial. The size varies from a pinhead to a pea. When we continue to zoom in, we can see the muscle fibers that make up the muscle. The lines on the muscle fibers represent sarcomeres. Millions of sarcomeres, acting like tiny pumps, have to contract to create movement. Sarcomeres can become overstimulated and unable to release their contracted state. This knot of contracted sarcomeres shows a segment of the fiber that has become shorter and wider because of this. But also a different segment now becomes stretched by this tension, shown by the greater distance between the sarcomeres. Together, multiple of these sarcomere knots form the trigger point. The stretched segments of the fibers give tightness to the taut band in which the trigger point lies. When sarcomeres are stuck in contraction, blood flow stops in the immediate area. The resulting oxygen starvation and accumulation of waste products irritate the trigger point. The trigger point responds by sending out pain signals. In return, your brain will stimulate you to stop using the muscle, which further shortens and tightens up the muscle. Trigger points will not release without proper treatment. The most effective way to treat a trigger point is applying deep stroking massage directly to the trigger point. This can be done without the help of others. Deep stroking massage means performing a series of deep strokes across the trigger point nodule. In this example, a rubber bouncing ball is placed between the body and the wall to reach the trigger point in the lower trapezius on the back side of the body. You can see the ball moving slowly and deeply in short strokes from one side of the trigger point to the other. Series typically consist of about 8 to 12 strokes and are performed about 5 to 10 times a day. By using deep stroking massage, you are milking the trigger point, so to speak. Blood and lymph fluid is moved out containing waste generated by the contracted muscle fibers. Each time you move over the trigger point and release the pressure, fresh blood immediately flows in, bringing fresh oxygen and nutrients. It may take several weeks to return the muscle fibers to their normal state and fully release the trigger point. Trigger points which have existed for a long time will take a lot of treatment, but often results can be achieved in days, meaning less pain and improved mobility. You can find references to more in-depth information about trigger points and their treatment in the video description below.
Wasn't that great? Dan found that somewhere, searching the internet probably, because he has nothing else to do, right? Yes, love the video, great. I have trouble hearing it on this end. I don't know if you guys did, but my speaker just doesn't like that video. All right. Oh, that's the end of our lesson. Let me see what videos we haven't seen. Let's see, I'm gonna look at a couple. I have two here that I didn't show you. Let me see how long they are. No, this is a double. That one was a double, so I'll have to figure out which one that one was. And I guess I'll try this one right here. Oh, that's, oh, here, let's watch. This one's only 4 minutes.
The contraction of a skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, the functional unit of contraction is called The sarcomere. A sarcomere shortens when myosin heads in thick myofilaments form cross bridges with actin molecules in thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding sites on actin remain exposed, the cross-bridge cycle will repeat. And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
Hey, that was a good one, huh? That was a good one. I'm glad I searched through those and found that last one. Okay, someone's asking me to go back to the myasthenia slide, so I'm going to do that right now. And then I'm going to see if there's anything we can do in ABMP. The thing about ABMP, oh, I'm sorry. The thing about ABMP and muscles is that it's about the individual muscles and not about the pathology. So, but I'm going to go check really quick because we have 16 minutes left of class. And if anybody has any questions while I'm going, oh, rigor mortis slide. Okay, so is the person done with? Oh, you're welcome, June. Have a good afternoon. Does whoever wanted me to go to this slide, are you done? Or can I go to the rigor mortis one? Okay. All right, let me find rigor mortis. There you go. Can you
I
still
was going
see
to say
it?
no, it's my goal not to see rigor mortis for as long as I can.
Ah,
It's just a little joke.
so funny, Dan. I just can't get enough. ABMP. Yeah, I mean, the exam coach, I mean, I don't think good luck with the muscle contraction day, right?
Yeah, it seems like once in a while they'll give a good question in there, but yeah, you're right. Usually it's
Yeah,
not about muscle contraction. They should have a whole
maybe we
different
can
category.
find yeah, yeah. I mean, if they had a neuromuscular, that would make sense, but they don't. So Eric is asking about homework. Which chapter did you get the new? Did you get the new? You guys weren't you sent the new syllabus? Dan, do you know anything about that? Erica, you should have the new syllabus. Check your email. Everyone is saying that the new syllabus came out. Okay.
Yeah, I'm actually
And
looking
Dan,
at the new syllabus also. So,
yeah, because I don't know what
reading,
chapter offhand. But Erica, check your email.
yeah,
See, it's kinesiology. Let me look under pathology.
yeah. I think pathology might have something more.
Okay. Let's see. It might be more about injuries.
Keeping my fingers crossed here.
Okay, thank you. Come on. Yeah, this is not really what we study, but we can play with these. A common location for a tendinopathy, meaning your tendon is upset. Okay, it has some sort of a rip or a tear or a strain. Dan, are you actually sitting at your computer? All right, a lot of you are picking supraspinatus, so I'm going to choose that. Excellent. A common factor that may contribute to iliotibial band syndrome. Oh, I love wide hips. I love it. Wide hips. A common factor that may contribute to IT band syndrome. The email, Alexis, would have come from the school. Contact Laguna, I believe. Okay, a lot of you are picking, let me look, because I'm, excessive medial rotation of the hip is what a lot of you are picking, so I'm going to, nope, We'll go with the second most is B. Nope. Do you think it's wide hips or friction? Okay, friction. There you go.
I just emailed it to Alexis.
Okay, well, a few people are telling me they didn't see the email, even though we told them it was coming. Do you think you could upload it to the webinar?
I can try, but I'm not optimistic.
Naomi says friction on the IT band would be friction on the hips, friction on I'm trying to think of types of friction. So the friction be caused from the IT band gluing to other tissues and then it trying to move independent and it can't. Raquel, where did you get your syllabus? From the email from the office? Okay, is it the correct one though? Is it the correct one? You know what, I'm gonna close ABMP because I wanna solve this issue of the syllabus. So I'm gonna log out and we're gonna forget about this for today. And we're going to try to figure out this syllabus issue. The office sent out an email. It would have come from, yeah, see, Natalie is saying, and Cynthia, it came from the Laguna Hills office.
Oh, and she says it's also already in the new handouts, or in the handouts. So yeah, I'm looking at it. It looks like that's correct.
That is the new syllabus, Dan?
Yes. Very good.
On Wednesday. So I think the email went out on Wednesday.
So yeah, if you need the syllabus, just get it from the handouts.
Can you guys all see the handouts on your? Let me open it up. Oh, updated. So you guys don't even have to print this. You can just go to the handouts and here's the updated syllabus that Dan and I created on Monday. It's in the webinar. I just opened it and now you can save it to your computer, right, Dan?
Correct.
So you don't even have to have the office print it. This is the new syllabus. So the homework, you'll be reading chapter 7, chapter 8, pages 234 and 235. So we spelled out some specific things. So chapter 7 and chapter 8, and then these 2 pages in particular. It says I already have it. You emailed it to us. Well, I didn't, but the office would have. So Raquel, can you open the handout? On the webinar?
In the control panel.
In the control panel. Dan, you go ahead and take over. My throat is killing me.
Okay. Yeah, it's either with me it's just basically an arrow you pull down. There's 3 handouts in there: a skin handout, syllabus, and updated complete packet. just click on the syllabus one and it opens it up. It's a PDF. All right, good deal. You got it. Excuse me. Is there anyone else that had an issue with that? That's what I did on Wednesday. Very good. Perfect. You got it. No. No, nobody is having any issues, correct? I'm going to say. Any other questions? No. We're good. All right, it is 3:56. I searched
Oh,
for my
there's
emails.
Erica.
Okay, Erica, you don't need to look for your email. It's here in the handouts within the control panel. Okay, all you have to do is click on it from the handouts, which I had on there Wednesday. And, you know, memory is the second thing to go, so I completely forgot I even loaded it.
I know, right? So Erica, are you on a computer? Can you open the handouts? Can you get the syllabus and save it on your computer?
Oh, here, Erica.
She's on her phone. Dan, can you email it to her?
I am hitting the send button as we speak.
All right. Thank you guys for today. Muscle contraction is amazing. And you're welcome. And Dan, thank you. Logging out. Go ahead and log out. I'll see you guys next Sunday for Nerve Day.
See you guys Wednesday.
Now this is different, huh, Dan?
What's that?
People actually logging out.
You know, on Wednesday, everybody logged out except for one student, and luckily he was a circulatory student. So I talked to him about it, and he was on two different devices, and it said I couldn't log him even out at all because he had logged out of one device, and that's why it still showed up on the other one.
Oh,
You know what I mean?
yeah.
So there are a few people. Yeah, have a good rest of your weekend, I guess. Have a good Sunday night, and see you Wednesday. So sign out, the people that haven't.
Corey and Isaac, are you there? There's Corey. Go ahead and sign out. Okay, leaving now. Bye. Red X, yeah. So where's Isaac?
Isaac. Yeah, it shows him non-attentive too.
Do you know
Okay,
Isaac?
well, I'm going to dismiss him. Okay, he's gone.
Do you know Isaac?
No, the only thing I know him